Tonight we're going to talk about the most violent magnets in the universe and the night one of them reached across the galaxy to brush against our sky. It is a strange thing to begin a story with an ending that almost no one remembers. December 27th, 2004. 2 days after Christmas. The Indian Ocean was still reeling from the tsunami that had struck on Boxing Day, and the world's attention was fixed on coastlines half a world away, on the unimaginable scale of loss unfolding in real time across Indonesia, Sri Lanka, Thailand, and a dozen other nations. The news was filled with water, with grief, with the particular helplessness that comes when the Earth itself seems to have turned against us. And so almost no one noticed that on that same night something else happened. Something quieter, in a sense. Something that left no visible wreckage, claimed no lives, and vanished from the instruments that detected it before most of the scientists monitoring those instruments had even finished their morning coffee. But it was, in its own way, one of the most extraordinary events in the recorded history of human observation of the cosmos. And it came from so far away that the light announcing it had been travelling since before our species existed. Picture, if you can, the network of satellites circling our planet in those last days of 2004. Dozens of them, strung like beads on invisible threads around the Earth, each one carrying instruments designed to listen to the sky in wavelengths our eyes cannot see. Gamma rays, X-rays, the hard, energetic light that streams from the most violent corners of the universe, from collapsing stars and feeding black holes, and the incomprehensible machinery of galactic nuclei. These satellites are our sentinels. They watch for flashes that might tell us something about the physics of extremes, about the deaths of stars, about the nature of matter crushed beyond all ordinary understanding. On the night of December 27th, every one of those sentinels went blind at the same moment. It happened so fast that the satellites themselves did not understand what was occurring. Their detectors, carefully calibrated to count individual photons of high-energy light, were suddenly flooded. One NASA engineer would later describe it as trying to fill a drinking glass with a fire hose. The instruments were not designed to handle this. They could not count fast enough. They could not process fast enough. Within a single millisecond, a thousandth of a second, the detectors aboard NASA's newly launched Swift satellite were overwhelmed. ESA's Integral Observatory, orbiting high above the Earth's atmosphere to get a cleaner view of the gamma-ray sky, suffered the same fate. RESI, a spacecraft built specifically to study solar flares, was saturated for half a second, its sensors simply unable to keep up with the torrent of energy pouring in from somewhere beyond the sun. The satellites did what satellites are programmed to do when they encounter conditions outside their expected parameters. They protected themselves, automatic safe modes engaged, instruments shut down or switched to lower sensitivity configurations. Ground controllers at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and at the European Space Operations Center in Darmstadt, Germany, began to receive telemetry indicating that something unusual had occurred. But the data itself was, at first, almost useless. The instruments had been so thoroughly overwhelmed that the initial spike of the event was clipped, saturated, unreadable in its true intensity. It was like trying to measure the brightness of an explosion by looking at the charred remains of the light meter, and yet within hours the pieces began to come together. The timing was the first clue. Every satellite that had been blinded at the same instant, or close enough to the same instant that the differences could be accounted for by the light travel time between their different positions in orbit. Whatever had caused this, it had not come from the sun. It had not come from anywhere nearby. It had come from the same direction in every case, and it had arrived at Earth as a single, coherent wave front of gamma-ray light. The second clue was the shape of the signal itself. After that initial overwhelming spike, the moment when the detectors simply gave up trying to count, there was a tail, a long, slowly fading afterglow of X-ray light that persisted for hundreds of seconds, and within that tail there was a rhythm, a pulse, a beat. The light was flickering, rising and falling with a period of roughly 7.5 seconds, as regular as a heartbeat. The scientists knew what that meant. That rhythm was the signature of a rotating object, something compact, something dense, something spinning once every 7.5 seconds and, with each rotation, sweeping a beam of radiation across the sky like the beam of a lighthouse. It was a neutron star. But it was not just any neutron star. The energy involved was too extreme. The spectrum of the light was wrong. The location in the sky matched a known source, an object that had been flickering and flaring for years in a part of the constellation Sagittarius. An object designated in the dry language of astronomical catalogues as SGR 1806-20. SGR stands for Soft Gamma Repeater. It is a name that sounds almost gentle, almost clinical. It gives no hint of what these objects truly are. To understand what happened on the night of December 27th, 2004, we must first understand what a magnetar is, and to understand a magnetar, we must start with its parent, the neutron star. When a massive star dies, a star perhaps 10 or 20 or 30 times the mass of our Sun, it does not go quietly. The core of the star, the dense heart where nuclear fusion has been fighting against gravity for millions of years, finally exhausts its fuel. There is nothing left to burn, nothing left to push back against the crushing weight of the star's own mass, and so the core collapses. It happens in less than a second. A ball of matter perhaps the size of Earth, containing more mass than the Sun, simply falls in on itself. The collapse releases an almost unimaginable amount of energy. The outer layers of the star are blasted outward in a supernova explosion, scattering newly forged elements across light years of space. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it cooked in the hearts of dying stars and scattered by their final moments. But the core does not explode. The core keeps falling. And then something remarkable happens. The electrons and protons in the collapsing core are squeezed together with such force that they merge, combining to form neutrons. The core becomes a ball of neutronium, matter so dense that a teaspoonful of it would weigh as much as a mountain on Earth. The collapse is finally halted, not by the pressure of heat or the resistance of atoms, but by the quantum mechanical principle that forbids neutrons from occupying the same space. The core stabilizes. What remains is a neutron star. A neutron star is an almost impossible object. It is typically about 20 kilometers across, roughly the diameter of a small city, but it contains more mass than the entire Sun. The density is beyond comprehension. If you could somehow stand on the surface of a neutron star, the gravity would be 200 billion times stronger than Earth's. A marshmallow dropped from a height of 1 meter would strike the surface with the force of a nuclear bomb. But here is the thing about neutron stars. When the core of the parent star collapses, it does not just compress the matter. It also compresses the magnetic field. And magnetic fields, like many things in physics, do not take kindly to being squeezed. Imagine you have a ball of yarn, and wound through that yarn is a single thread of something else. A wire, perhaps, carrying a current. Now imagine you take that ball and crush it down to the size of a marble. The wire has nowhere to go. It is forced into smaller and smaller loops, concentrated into a tighter and tighter space. The magnetic field of the original star, which might have been perfectly ordinary, not so different from the Sun's, is now packed into a sphere 20 kilometers wide. And the strength of a magnetic field depends on how tightly packed it is. An ordinary neutron star has a magnetic field perhaps 1 trillion times stronger than Earth's. This is already extraordinary. But some neutron stars are born different. Some, through processes that are still not entirely understood, emerge from the supernova with magnetic fields that are 1,000 times stronger still. These are the magnetars. The name was coined in the early 1990s by 2 physicists, Robert Duncan, then at the University of Texas, and Christopher Thompson, at the Canadian Institute for Theoretical Astrophysics. They had been puzzling over a class of objects that did not quite fit the existing models. Neutron stars that flared and flickered in ways that could not be explained by the usual mechanisms of rotation and accretion. Objects that seemed to be powered by something other than spin or in falling matter. Duncan and Thompson proposed that these objects were neutron stars with magnetic fields of truly staggering intensity, fields of 10 to the 15th power Gauss, or even stronger. A quadrillion times the strength of Earth's magnetic field, so strong that the field itself becomes a source of energy. So strong that the crust of the neutron star, yes, neutron stars have crusts, thin shells of relatively normal matter floating atop the sea of neutronium beneath, cannot contain the stresses. And when the crust finally cracks, the Magnetar screams. The theorists predicted years before it was observed that magnetars would occasionally release bursts of energy, starquakes in a sense, as the crust shifted and the tangled magnetic field lines snapped and reconnected. These bursts would be brief and intense, releasing more energy in a fraction of a second than the sun puts out in years. They called them giant flares. On December 27, 2004, the universe provided a demonstration. SGR 1806-20 had been known to astronomers since 1979. It had been flickering and flaring for decades, a repeating source of soft gamma rays that occasionally brightened and then faded. But on that December night, it did something it had never done before, something that exceeded anything the theorists had dared to predict. The flare lasted in its most intense phase for about 0.2 of a second, 1/5 of a heartbeat. In that eye blink of time, the Magnetar released as much energy as the sun puts out in 250,000 years. Let that number settle for a moment. 250,000 years of sunlight compressed into the span of a single human breath. The total energy of the flare was approximately 2 × 10 to the 46th power ergs. That notation, 10 to the 46th, can slide past without leaving an impression. So let us try to make it real. 10 to the 33rd ergs is about the energy output of the sun over its entire main sequence lifetime, 10 billion years of steady hydrogen burning. The Magnetar flare was 10 trillion times more energetic than that. It was 100 times more luminous than the 2 previous giant flares on record, which had themselves been among the most energetic events ever observed from beyond the solar system. And here is what makes this story strange. What makes it, in a sense, a story about us. SGR 1806-20 is not close. It is not in our cosmic neighbourhood. Not. It is not lurking in the outer reaches of the solar system, or drifting through the sparse stars between here and Alpha Centauri. It is on the far side of the Milky Way galaxy, in a region called the Scutum Centaurus Arm, where the galaxy's spiral structure curves away into the deep background of the cosmos. The best estimates place it somewhere between 40,000 and 50,000 light-years from Earth, halfway across the entire galaxy. The light that reached us on December 27, 2004, had been travelling since before anatomically modern humans existed. It left the Magnetar when our ancestors were still sharing the planet with Neanderthals, when mammoths roamed the northern steppes, when the ice ages were a present reality rather than a distant memory. 50,000 light-years. It is a distance that ought to provide comfort, a distance that ought to mean safety. What could possibly reach across such a gulf? And yet, the flare from SGR 1806 did not merely saturate the detectors aboard a handful of scientific satellites. It did not merely blind our instruments for a fraction of a second. It reached down through the emptiness between the stars, across the unimaginable darkness of interstellar space, and it touched our planet. It touched the thin shell of electrically charged gas that floats at the top of our atmosphere, the ionosphere. The ionosphere is not something most people think about in their daily lives. It is too high to see, too thin to feel, too abstract to worry about. But it is there, 100 kilometers above your head, a tenuous layer of atoms that have been stripped of their electrons by the constant bombardment of ultraviolet light from the sun. It is the ionosphere that makes long-distance radio communication possible, bending and reflecting radio waves around the curve of the Earth. It is the ionosphere that glows with the green and red curtains of the aurora when charged particles from the sun spiral down along Earth's magnetic field lines and collide with atmospheric gases. Under normal circumstances, the ionosphere responds to the sun. The sun rises, the ultraviolet flux increases, the ionosphere thickens and rises. The sun sets, the ultraviolet fades, the ionosphere thins and sinks. There is a rhythm to it, a daily pulse that has been beating since the Earth first developed an atmosphere capable of being ionized. On December 27, 2004, that rhythm was interrupted. For a few minutes, in the middle of the night, when the ionosphere should have been at its thinnest and lowest, relaxed in the absence of solar ultraviolet, something changed. The D layer, the lowest region of the ionosphere, which normally all but disappears after sunset, suddenly flickered into existence. It thickened. It responded as if the sun had suddenly risen, had suddenly flooded the night sky with far more ultraviolet than any sunrise could provide. It was responding to the Magnetar. 50,000 light-years away, a crust had cracked. A magnetic field had screamed, and the echo of that scream had ionized our atmosphere. Think about what this means. Think about the scale of it. The sun is 8 light-minutes away. Its light arrives at Earth fresh, still warm from the nuclear furnace. And yet the sun, for all its power, the sun that sustains every living thing on this planet, the sun that drives our weather and our seasons and the very chemistry of life, the sun cannot, under normal circumstances, ionize the nighttime D-layer from the far side of the Earth. The Magnetar did it from 50,000 light-years away. This was not supposed to happen. In the models, in the predictions, in the comfortable assumptions of astrophysics, objects on the far side of the galaxy were supposed to be too far away to matter. They were supposed to be abstractions, points of light in a catalogue, names in a database. They were not supposed to reach through the dark and brush their fingers against our sky, but they did. One of them did. And the quiet question that has haunted a small community of scientists ever since is this. If something that far away could ionize our upper atmosphere, what would something closer do? We will return to that question. We will turn it over slowly, examine it from different angles, follow it down into the mathematics and out the other side into the strange territory of probability and risk. But first, let us stay a while longer in that December night. Let us sit with the moment itself before we begin to ask what it means. The satellites that detected the flare were, in their own way, survivors. They had been built to study the gamma-ray sky, but they had not been built to survive an assault like this. The fact that they came through with their instruments intact was, in part, a matter of engineering, and in part a matter of luck. The detectors were saturated, yes, they were overwhelmed, but they were not destroyed. The photons that poured in from SGR 1806-20 were energetic, but they were not infinite. The instruments recovered. The data, though clipped at the peak, was still there in the tail, and what a tail it was. For 600 seconds after the initial spike, 10 full minutes, the Magnetar continued to glow. The X-ray light pulsed with that steady 7.5-second rhythm, the lighthouse sweep of a neutron star spinning in the dark. The pulse period was precise, 7.56 seconds, and within the envelope of that pulsation there were finer structures, oscillations, wobbles. The neutron star was ringing like a bell, its crust still quivering from the violence of the flare. Scientists studying the aftermath would later identify these oscillations as seismic waves propagating through the neutron star's crust. Starquakes. The crust of a neutron star is not like any material we know. It is thought to be a crystalline lattice of neutron-rich nuclei, held together by the immense pressure of the layers above and below. It is stronger than any material that can exist under normal conditions, strong enough to resist the tidal forces that would tear an ordinary planet to shreds. But even this material has limits, and when a Magnetar's magnetic field twists and snaps, those limits are exceeded. The December 27th flare was, in essence, the sound of a neutron star's crust breaking. If that sounds violent, it is. But it is also, in a strange way, beautiful. The physics of Magnetar flares involve some of the most extreme conditions in the observable universe. Temperatures of billions of degrees. Magnetic fields so strong that they distort the very atoms that dare to exist within them, stretching electron orbits into elongated tubes, forcing matter to behave in ways that have no analogue in any laboratory on Earth. And yet, for all that violence, the light that reaches us is information. It is a message, written in the language of photons and arrival times and spectral shapes. It tells us about the structure of matter in conditions we could never hope to replicate, about the behaviour of fields that would vaporize any probe we might send to study them. The Magnetar does not know we are listening. It does not know that its scream, 50,000 years in transit, would arrive at a small blue planet in an unremarkable arm of the galaxy, where curious primates would build instruments to catch its light and spend years puzzling over its meaning. The Magnetar is indifferent. It is a remnant, a cinder, the compressed core of a star that died before the first stone tools were chipped from flint. It screams because that is what Magnetars do. It screams, and the universe carries the sound. And we, for a few minutes on a December night, were close enough to hear. The researchers who studied the event in the weeks and months that followed were, by all accounts, somewhat stunned by what they had found. The energy release was so far beyond the previous records that it required revisions to the theoretical models. The magnetic field strength implied by the flare, more than 10 to the 16th Gauss, perhaps significantly more, pushed the Magnetar into a regime that had been considered extreme, even by the standards of extreme objects. SGR 180620 was not just a Magnetar. It was quite possibly the most powerful magnet in the known universe, and it had been there all along, flickering in the dark, waiting for the moment when its crust would slip, its field would snap, and its voice would carry across the light years to brush against the edge of our world. There is something worth pausing on here before we move forward. Something about the nature of distance, and the illusion of safety it provides. When we think about threats from space, and humans do think about such things from time to time, usually after a movie or a news story about an asteroid, we tend to think in terms of proximity. The asteroid that might strike Earth is dangerous because it is close, because its orbit brings it near us, because the mathematics of celestial mechanics have conspired to put it on a collision course. The comet that might someday tumble in from the outer solar system is dangerous for the same reason. These are objects whose threat is a matter of geography, of shared space, of the unfortunate coincidence of two paths crossing at the same moment. But the Magnetar is different. The Magnetar does not need to come close. It does not need to share our space. It sits on the far side of the galaxy, and its violence reaches us anyway. The speed of light, the fastest speed there is, the universal limit that nothing with mass can exceed, is not a barrier to the Magnetar's influence. It is a carrier. The light brings the violence with it, crossing the gulf of interstellar space at 300,000 kilometers per second, and when it arrives with all the energy it had when it left. This is perhaps the most unsettling thing about the December 27th event. Not the scale of the flare itself, though that is staggering. Not the fact that it ionized our atmosphere from 50,000 light-years away, though that is remarkable. It is the realization that the universe does not care about our intuitions of distance. The rules we live by, the sense that far away means safe, that the dangers of space are measured in orbital trajectories and approach velocities, those rules do not apply to everything. Some things can reach out across light years and touch us without ever coming close. The Magnetar did not visit our solar system on December 27, 2004. It did not send a tendril of plasma or a cloud of debris. It simply released a burst of energy, as it had done before and would do again, and the geometry of the universe happened to point that burst in our direction. That was all, a crack in a crust, a scream in the dark, and a distant planet caught for an instant in the beam. We were lucky, in a sense. The distance was so great that the effects, though measurable, were not catastrophic. The ionosphere flickered, the satellites recovered, the world, preoccupied with a tragedy of a different kind, barely noticed. But the question lingers. It floats there in the background of every subsequent observation, every catalogue entry, every survey of the neutron star population. If that Magnetar at that distance could reach us, what else is out there? What other objects, closer and quieter, might be waiting to flare? What would happen if the next one were not 50,000 light-years away but 10,000? Or 1,000? Or 100? We will explore these questions together, slowly, in the hours ahead. We will walk through the census of known Magnetars and the statistical shadows of the ones we cannot see. We will trace the history of mass extinctions and the quiet, persistent suspicion that some of them may have arrived from above. We will stand at the edge of what is known and look out into the uncertainty that surrounds it. But for now, let us simply hold this moment. December 27, 2004. The satellites blinded. The ionosphere stirred. The evidence of a violence so extreme, from a distance so great that it challenges our sense of what is and is not too far away to matter. The Magnetar does not know we exist. It has no awareness, no intention, no malice. It is a relic, a remnant, a slowly cooling ember of a star that died long ago. But it demonstrated something that night. It proved, in the language of photons and saturated detectors, that the universe is smaller than we thought. That distance is not always protection. That the quiet dark between the stars is not as empty as it seems. And somewhere out there, in the vast rotating disk of the Milky Way, there are other Magnetars, ones we have found, ones we have not. Some of them are pointed elsewhere, their beams sweeping past us without effect, their flares invisible from our vantage point, But some of them, statistically speaking, must be pointed toward us. Some of them must be closer than SGR 180620. The question is not whether another giant flare will occur, Magnetar's flare. It is what they do. The crust cracks, the field snaps, the light screams outward at the speed of causality. The question is where. The question is when. The question is whether we will be in the beam when it happens. This is the story we are going to tell tonight. A story of magnetism and distance, of violence and probability, of the quiet risks that hang above us in a sky we think we understand. It is not a story with a simple ending, because the ending has not been written yet. It is happening now in the slow tick of cosmic time, in the gradual decay of magnetic fields, and the patient accumulation of stress in crusts we cannot see. But before we go further, before we start asking how, close is too close, before we begin counting the magnetars and measuring the distances, we should take a moment to simply be present with what we have learned. On December 27, 2004, something reached across 50,000 light-years of empty space and touched our sky. It came from a dead star smaller than a city. It lasted less than a second, and it left behind a question that we are still trying to answer. Tonight, we're going to sit with that question. We're going to follow it where it leads, through the physics of impossible objects and the statistics of unseen threats and the strange, quiet calculus of cosmic risk. And when we reach the end, or as close to an end as a story like this can have, perhaps we will understand something we did not understand before. Not about magnetars necessarily, though we will learn about those too. But about the nature of the sky above us, about the invisible dangers that share our universe, about the particular and peculiar privilege of being alive on a planet that has so far been lucky. The magnetar is still out there. It is still spinning, still cooling, still nursing the tangled field that will one day crack again. It does not know we are here, it does not care, but we know it is there, and that knowledge, once gained, cannot be ungained. So let us begin. The ionosphere flinched. That is not a metaphor. It is not a poetic flourish designed to make an abstract phenomenon feel more immediate. It is a precise description of what happened on December 27th, 2004, and the fact that we can say it with such certainty, that we can point to the data and trace the exact moment when our planet's atmosphere physically responded to an event on the far side of the galaxy, is one of the most quietly astonishing details in all of modern astrophysics. To understand what happened, we need to descend from the realm of gamma rays and saturated satellites into something more humble, something that hums along beneath our feet and above our heads every day, unnoticed, unremarked, carrying the quiet commerce of radio signals from one side of the world to the other. We need to talk about very low-frequency radio waves. VLF signals occupy a peculiar niche in the electromagnetic spectrum. They are too low in frequency for ordinary radio broadcasts, too slow for the rapid chatter of modern communications. But they have a gift that higher frequencies lack. They can travel enormous distances by bouncing between the Earth's surface and the lower edge of the ionosphere, that thin shell of electrically charged particles that begins about 60 kilometers above our heads. The ionosphere acts as a kind of ceiling, and VLF signals skate along beneath it like stones skipping across the surface of a very still pond. Military submarines use them. Scientific instruments monitor them, and on any given night, if you have the right equipment, you can listen to them whispering their way around the curve of the planet. One such signal originates from a transmitter in Lualuale, Hawaii. It broadcasts at 21.4 kHz, a frequency so low that each wave stretches nearly 14 kilometers from crest to crest. The signal is picked up at Palmer Station, Antarctica, more than 13,000 kilometers away, after bouncing its way across the Pacific and the Southern Ocean. It is a routine measurement, part of a global network of VLF monitoring stations that track the behavior of the ionosphere for research purposes. The data flows in continuously, day after day, year after year, a quiet heartbeat of information about the electrical state of the upper atmosphere. On the night of December 27, 2004, at 21:30:26 Universal Time, that heartbeat stuttered. The researchers who first noticed it were affiliated with Stanford University's STAR laboratory, a group that had spent years developing techniques for using VLF signals as a kind of diagnostic tool for the ionosphere. Among them was Umran Inan, a professor of electrical engineering who had devoted much of his career to understanding the complex dance between electromagnetic waves and the charged particles of the upper atmosphere. When the data from that night came in, it showed something unprecedented. The signal from Hawaii had changed, not gradually, not in the slow drift that characterizes normal ionospheric variation, but suddenly, dramatically, in a way that made the instruments look as though they had malfunctioned. The amplitude of the signal, a measure of its strength, had jumped by more than 26 decibels. The phase, a measure of the timing of the wave crests, had shifted by 328 degrees. These are not small numbers. They represent a massive, violent perturbation in the electrical properties of the ionosphere, the kind of change that normally only occurs when the sun rises and floods the upper atmosphere with ultraviolet light. But the sun had not risen. It was night over the Pacific. The ionosphere should have been quiet, settled into its nocturnal state, the electrons in the D layer, the lowest portion of the ionosphere, about 60 kilometers up, sparse and calm. Instead, the data showed that the electron density at that altitude had increased by a factor of roughly 100. In the space of 200 milliseconds, less than the time it takes to blink, the nighttime ionosphere had begun behaving as though it were experiencing a sudden intense dawn. And then, just as suddenly, the cause became clear. The timing matched exactly. The perturbation had begun at the precise moment when the gamma-ray detectors on the satellites overhead had been overwhelmed by the flare from SGR 1806-20. The Magnetar's light, racing across 50,000 light-years of empty space, had arrived at Earth and dumped its energy into the upper atmosphere. The gamma rays had ionized the neutral molecules in the D layer, stripping electrons free, creating a sudden spike in conductivity that altered the way VLF signals propagated. The ionosphere had flinched because something had reached down from the other side of the galaxy and touched it. The perturbations were not limited to the Hawaii-Antarctica path. Researchers at the University of Louisville, Kentucky, detected similar anomalies in their VLF data. The British Antarctic Survey recorded the same sudden shifts. Across the sunlit hemisphere of the Earth, the side that happened to be facing the direction of the Magnetar at that moment, the ionosphere had responded in unison to an event that had occurred before the first anatomically modern humans walked the Earth. What struck the researchers most, in the days and weeks that followed, was not the initial perturbation, it was the recovery, or rather, the slowness of the recovery. Umran Inan, presenting the findings at the American Association for the Advancement of Science meeting in February 2006, put it simply. The remarkable thing was that it took an hour for the ionosphere to come back from this disturbance. An hour. The flare itself had lasted a fraction of a second. The initial spike in the VLF data had occurred in 200 milliseconds, but the enhanced conductivity, the elevated electron density, the altered state of the upper atmosphere, these persisted for more than 60 minutes. The ionosphere had been knocked out of its equilibrium, and it took that long for the excess electrons to recombine, for the charged particles to settle back into their normal nocturnal configuration, for the sealing of the VLF waveguide to return to its usual height and density. This is the detail that makes the event feel real. Not the numbers on the satellite detectors, not the calculations of energy output, not even the knowledge that the Magnetar was impossibly far away. It is the hour. It is the fact that our atmosphere, the thin envelope of gas that separates us from the vacuum of space, was measurably disturbed for more than an hour by a burst of light that lasted less than a second, from a source that would take a beam of light 50,000 years to reach. The ionosphere flinched, and then it spent an hour recovering its composure. This remains, to this day, the only confirmed instance of an extragalactic object visibly altering Earth's atmosphere. There have been other cosmic events, other bursts of radiation from distant sources, other moments when the sky has briefly flared with light from beyond our solar system, but none of them have left a measurable fingerprint on our planet in quite this way. The December 27th flare is unique in the scientific record, a moment when the vast distances of the cosmos collapsed, when something from unimaginably far away reached out and physically changed the conditions on our world. The change was not harmful. The ionization occurred high in the atmosphere, far above the altitude where we live and breathe. No one on the ground felt anything. No one looked up and saw the sky brighten. The event passed unnoticed by everyone except the instruments designed to detect it and the researchers trained to interpret their data. But the fact that it happened at all, the fact that we can point to the charts and say, here, at this moment, the ionosphere responded to a Magnetar flare from across the galaxy, that fact carries a weight that is difficult to put into words. It means the threat is not abstract. It means the distances involved, however vast they may seem, are not sufficient to guarantee our isolation. It means that when we talk about magnetars and their potential effects on Earth, we're not engaging in speculation or science fiction. We're talking about something that has already happened, something that left its mark in the data, something that proved the universe is capable of reaching out and touching us in ways we had not anticipated. And that brings us to a harder truth, a truth about the nature of discovery, about the history of astrophysics, about the unsettling pattern that runs through our understanding of the violent universe. We almost never see these things coming. Consider for a moment the story of gamma-ray bursts themselves. Before December 27, 2004, before SGR 1806-20, before anyone had heard the term Magnetar, there was a different mystery. A mystery that began not with astronomical observations, but with nuclear paranoia. It was 1963, and the world was holding its breath. The United States and the Soviet Union had just signed the Nuclear Test Ban Treaty, an agreement that prohibited the testing of nuclear weapons in the atmosphere, in outer space, and underwater. The treaty was a fragile thing, born of fear and negotiation, and neither side fully trusted the other to honour it. The Americans, in particular, worried that the Soviets might attempt to conduct secret nuclear tests in space, detonations that would be invisible from the ground but that might be detected by the right instruments. And so the Vela satellites were born, a constellation of spacecraft launched in pairs, designed to monitor the Earth and its surroundings for the telltale signature of nuclear explosions, the distinctive double flash of gamma radiation that accompanies the detonation of an atomic weapon. The satellites were not built for astronomy. They were built for surveillance, for verification, for the grim calculus of mutually assured destruction. They stared outward into the dark, waiting for a flash that they hoped would never come. On July 2nd, 1967, the flash came, but it was not what anyone expected. The Vela satellites detected a burst of gamma radiation, intense, brief, unmistakable, but it did not match the profile of a nuclear explosion. The timing was wrong. The spectrum was wrong. The direction was wrong. It seemed to come not from Earth or its vicinity, but from somewhere out in deep space. The analysts at Los Alamos National Laboratory, poring over the data, could not explain it. They filed it away and continued their watch. More bursts followed. Over the next few years, the Vela satellites detected dozens of them, each one a brief flare of gamma radiation from an unknown source in an unknown direction. The events were clearly real. The instruments were functioning properly, the detections were consistent, but their origin remained a complete mystery. Were they some new form of solar activity? Were they reflections from distant nuclear tests that had somehow escaped notice? Were they something else entirely? Something no one had imagined? The answer, when it finally came, was stranger than any of those possibilities. In 1973, a team led by Ray Kleber-Seidel of Los Alamos published the first academic paper on the phenomenon. The bursts, they concluded, were coming from outside the solar system. They were cosmic in origin, the signatures of some unknown process occurring at distances that could not yet be determined. The paper opened a new chapter in astrophysics, a chapter that would eventually reveal gamma-ray bursts to be among the most energetic events in the universe. The death cries of massive stars, the collisions of neutron stars, the birth pangs of black holes. But the point, for our purposes tonight, is not what gamma-ray bursts turned out to be. The point is how they were discovered. They were found by accident, by instruments designed for an entirely different purpose, by analysts who had no framework for understanding what they were seeing. The universe had been producing these bursts for billions of years. They had been washing over the Earth since before life emerged from the oceans, and we had no idea they existed until we stumbled upon them while looking for something else. The same pattern repeats itself throughout the history of astrophysics. Consider pulsars. In 1967, the same year the Vela satellites detected their first gamma-ray burst, a young graduate student at Cambridge University was reviewing data from a radio telescope designed to study quasars. Her name was Jocelyn Bell Burnell, and she was looking for the characteristic twinkling of distant radio sources caused by the solar wind. What she found instead was something entirely unexpected, a series of radio pulses arriving with extraordinary regularity once every 1.37 seconds, like the ticking of a cosmic clock. The pulses were so regular, so precise, that Bell Burnell and her advisor, Anthony Hewish, could not immediately explain them. No known natural phenomenon produced such a consistent signal. The regularity suggested something artificial, something engineered, something that might, just possibly, be the beacon of an extraterrestrial civilization. Half in jest, half in genuine uncertainty, they labelled the source LGM-1. Little Green Men. It was not, of course, a message from aliens. Further observations revealed more sources with similar characteristics, each pulsing at its own distinctive rate, scattered across the sky in a pattern that suggested a natural phenomenon rather than a deliberate transmission. The sources were eventually identified as pulsars, rapidly rotating neutron stars, the collapsed cores of dead suns, sweeping beams of radio waves across the cosmos like lighthouse beacons. The discovery revolutionized our understanding of stellar evolution and earned Hewish the Nobel Prize in Physics in 1974, though the omission of Bell Burnell from that honour remains one of the most controversial decisions in the history of the prize. But once again, the point is not the science that followed. The point is the moment of discovery, the moment when something entirely unexpected appeared in the data, something that did not fit any existing category, something that forced the observers to consider possibilities, including extraterrestrial intelligence, that they would never have entertained under ordinary circumstances. The universe had been full of pulsars for billions of years. They had been beaming their signals across the galaxy since before the Earth formed, and we had no idea they existed until a graduate student noticed an anomaly in her printouts. Gamma-ray bursts, pulsars, magnetars. The pattern is consistent and it is humbling. The most violent phenomena in the universe, the events capable of releasing more energy in a fraction of a second than our sun will produce in its entire lifetime, have a habit of revealing themselves only after they have already touched us. We do not predict them. We do not anticipate them. We stumble upon them, often by accident, often through instruments designed for entirely different purposes, and then we spend years or decades trying to understand what we have found. This pattern carries an implication that is difficult to avoid. If the history of astrophysics teaches us anything, it is that our catalogue of cosmic phenomena is almost certainly incomplete. The things we know about, the gamma-ray bursts, the pulsars, the magnetars, are the things we have happened to detect. They are the phenomena that have, by chance or by proximity, made themselves visible to our instruments. But what about the phenomena we have not detected? What about the events that are occurring right now in some distant corner of the galaxy that we have no way of observing? What about the objects that exist but have not yet announced themselves? This is where the question of magnetars becomes particularly unsettling, because the truth is we have found very few of them. As of the most recent surveys, the confirmed population of magnetars in our galaxy numbers fewer than 30 objects. 30 in a galaxy containing hundreds of billions of stars, in a cosmic environment where massive stars are constantly being born and dying, where the conditions for magnetar formation must be met countless times over the age of the Milky Way, we have identified fewer than 30 of these objects. The number is almost certainly not a reflection of reality. It is a reflection of our limitations. Magnetars are difficult to detect. They do not shine steadily like ordinary stars. They do not emit the continuous radio beams of ordinary pulsars. They spend most of their time in relative quiescence, their magnetic fields slowly decaying, their surfaces cooling, their presence betrayed only by occasional bursts of X-rays or gamma rays that may or may not be pointed in our direction. A magnetar that is not actively flaring, a magnetar whose beam does not happen to sweep across our line of sight, a magnetar that is simply sitting quietly in the dark, nursing its impossible magnetic field. Such an object might be completely invisible to our instruments. These are the dark magnetars, the ones we have not found, the ones that exist, statistically speaking, in far greater numbers than the handful we have catalogued. They are out there, scattered through the disk of the galaxy, embedded in the spiral arms, drifting through the spaces between the stars. Some of them are old, their fields fading, their activity diminishing, their threat receding with each passing millennium. But some of them are young. Some of them are still wound tight with magnetic energy, still capable of the giant flares that can ionize atmospheres from across the galaxy. And we do not know where they are. The mathematics of the situation is not reassuring. If we have found 30 Magnetars, and if our detection methods are sensitive to only a fraction of the total population, then the true number of Magnetars in the Milky Way could be hundreds. It could be thousands. The estimates vary depending on the assumptions you make about formation rates and lifetimes and detection efficiencies, but even the most conservative models suggest that the objects we have found represent only a small sample of the objects that exist. And here is the thought that settles in, quietly, as the night grows later. If there are hundreds or thousands of Magnetars in our galaxy, and if we have found only 30 of them, then most of the Magnetars that exist are invisible to us. They are dark, they are quiet, they are waiting. Waiting is perhaps the wrong word. It implies intention, and Magnetars have no intention. They are not malevolent, they are not patient predators hiding in the cosmic underbrush. They are simply objects, governed by physics, following the laws of electromagnetism and gravity and nuclear matter without awareness or purpose. But the effect is the same. Somewhere in the galaxy, there are Magnetars we have not found. Some of them are pointed away from us, their flares invisible from our vantage point, their beams sweeping harmlessly through empty space. But some of them, by the simple statistics of random orientation, must be pointed toward us. Some of them must be closer than SGR 180620. And when they flare, not if, but when, because Magnetars flare, it is what they do, the light will arrive without warning. We will not see it coming. We never do. This is the lesson of the Vela satellites, and the Cambridge Radio Telescope, and the blinded detectors of December 27, 2004. The universe does not send advance notice. It does not file environmental impact statements. It does not wait for us to develop the instruments capable of detecting its most violent phenomena before it allows those phenomena to occur. It simply acts, according to its own laws, on its own timescales, and we are left to notice, or not, depending on whether we happen to be looking in the right direction with the right equipment at the right moment. The ionosphere flinched on December 27, 2004, because a Magnetar 50,000 light-years away released a burst of energy that had been travelling toward us since before the last ice age. The VLF signals stuttered and recovered, the satellites saturated and reset, the data was collected and analysed and published, and we added one more entry to our catalogue of known Magnetars. But the catalogue is incomplete. It will always be incomplete. And somewhere in the dark spaces between the stars, in the regions of the galaxy we have not yet surveyed, in the directions we have not yet looked, there are objects that could do what SGR 180620 did, and do it from much, much closer. The question is not whether they exist. The question is where they are. The question is how close. The question is what happens when the next one flares, and whether we will be in the beam when it does. These are the questions that will carry us through the rest of tonight's journey. But for now, let us simply sit with what we have learned. The ionosphere flinched. The instruments recorded it. The researchers published it. And the universe, in its vast indifference, continued on, spinning its Magnetars, building its magnetic fields, preparing the next flare that will race across the light years toward whatever happens to be in its path. We are here, we are listening. And the sky above us is full of things we have not yet learned to see. And so we return to the problem of seeing, or rather, the problem of not seeing. Because everything we have learned so far rests on a foundation that is, when you examine it closely, remarkably fragile. We know about SGR 180620 because it flared. We know about the ionosphere because it flinched. We know about the 30 Magnetars in our catalogue because each of them, at some point in the past few decades, did something loud enough to catch our attention. But what about the ones that have not flared? What about the ones that are, at this very moment, spinning quietly in the dark, their magnetic fields wound tight, their crusts intact, their energy locked away beneath surfaces we cannot see? This is the question that has occupied some of the most patient observers in modern astrophysics, and it leads us to a name worth knowing. Victoria Caspi is a Canadian astrophysicist at McGill University, and she has spent much of her career doing something that might seem, at first glance, unglamorous. She watches neutron stars. She monitors them, tracks their pulses, records their timing anomalies, catalogues their outbursts. She led a project using NASA's Rossi X-ray Timing Explorer and later the Swift Observatory to keep a kind of census, a running tally of the magnetars we know about and the behaviours they exhibit. Her work is meticulous, accumulative, and deeply attentive to the spaces between events. And what her work reveals, more clearly than almost anything else in the field, is the size of the gap between what we have found and what must exist. Consider the numbers, one more time, but slowly. Models predict hundreds to thousands of magnetars in the Milky Way. The estimates depend on assumptions about how often massive stars collapse, how often those collapses produce the right conditions for extreme magnetic field amplification, how long magnetars remain active before their fields decay. But even the most conservative calculations suggest a population far larger than our catalogue, and yet, as of now, we have confirmed fewer than 30 objects out of hundreds, 30 objects out of perhaps thousands. The ratio is striking, and it demands an explanation. The explanation is not that the other magnetars are hiding. It is not that they are cloaked or camouflaged or deliberately avoiding detection. The explanation is simpler, and in some ways more unsettling. Magnetars are only visible during active outburst phases. When they flare, they announce themselves. When they emit bursts and pulses and giant releases of energy, they light up in the X-ray and gamma-ray bands, and we notice them. But when they are quiescent, when they are not flaring, not bursting, not cracking, they emit almost nothing detectable at current sensitivity limits. They become, for all practical purposes, invisible. This is worth sitting with for a moment. A magnetar in its quiet phase is not emitting the kind of radiation our instruments are designed to catch. It may glow faintly in certain wavelengths, but that glow is often too dim, too distant, too easily confused with the background noise of a galaxy full of stars and gas and dust. Without an outburst to draw our attention, a quiescent magnetar is just another point of nothing in a sky full of nothing. It does not call out. It does not beacon. It simply exists, turning slowly, its magnetic field coiled and ready, its crust holding for now. And this creates a profound observational bias. The magnetars we have found are not a representative sample of all magnetars. They are the ones that happen to be active during the brief window of time in which we have been capable of looking. They are the ones that flared while our satellites were overhead, while our telescopes were pointed in roughly the right direction, while our instruments were sensitive enough to register the signal. For every magnetar that announced itself with a burst loud enough to saturate a detector, there may be dozens, hundreds, that remained silent, spinning in the dark, unrecorded and unconfirmed. Think of it this way. Imagine you're trying to count the fireflies in a meadow, but your only method of detection is to wait for one of them to blink. You sit in the dark with your notebook, and every time you see a flash you make a tally mark. By morning, you have counted 30 fireflies. But how many fireflies are actually in the meadow? You do not know. You cannot know, because some of them blinked while you were looking elsewhere. Some of them blinked before you arrived, and some of them perhaps did not blink at all during the hours you were watching. Not because they are incapable of blinking, but simply because the timing did not align. Your count of 30 is real, but it is not complete. It is a lower bound, not a census. This is the situation Victoria Caspi's work illuminates. Her surveys have given us the most detailed picture we have of the magnetar population, but that picture is necessarily incomplete. It captures the active ones, the loud ones, the ones that happen to do something dramatic during the decades we have been watching. It cannot capture the silent ones. It cannot account for the magnetars that formed 10,000 years ago and have been quietly spinning ever since, waiting for their next outburst, or for the ones that flared spectacularly in the year 1100 and have been quiescent ever since, invisible to every instrument we have built. The catalogue is a snapshot of activity, not a census of existence, and the gap between the two is vast. This is what researchers mean when they talk about the detection paradox. The very thing that makes magnetars dangerous, their capacity for sudden, violent energy release, is also the only thing that makes them visible. A magnetar that never flares is a magnetar we will never find, at least not with current technology. And a magnetar we never find is a magnetar we cannot account for, cannot track, cannot factor into our calculations of risk. It exists in the darkness between the stars, present but unrecorded, real but invisible. And there may be hundreds of them, there may be thousands. The mathematics of formation rates and lifetimes and detection efficiencies all point in the same direction. The objects we have found are the exceptions, not the rule. The rule is silence. The rule is darkness. The rule is that most of the magnetars in our galaxy have not yet announced themselves, and may not announce themselves for centuries, or millennia, or ever. And this brings us inevitably to the question of distance. Because if the magnetars we cannot see are scattered throughout the galaxy, then some of them must be closer than others. Some of them must be nearer to us than SGR 1806-20, which sits 50,000 light-years away in the Scutum Centaurus arm. The question is not whether closer magnetars exist. The question is how close is too close. The question is at what distance a flare like the one that ionized our atmosphere in December 2004 would cease to be a curiosity and become a catastrophe. This is the work of researchers like Brian Fields at the University of Illinois and Adrian Melott at the University of Kansas. They have taken the energy output of known magnetar flares, the staggering quantities we have already discussed, the energy equivalent of 150,000 years of solar output released in 1/10 of a second, and they have applied the mathematics of distance scaling. The inverse square law governs how radiation spreads through space. Double the distance, and the intensity drops to 1/4, halve the distance, and the intensity quadruples. It is simple physics, and it has very unsimple implications. The flare from SGR 1806-20 reached us from 50,000 light-years away, and it ionized the D layer of our ionosphere. The electron density at 60 kilometers altitude increased by orders of magnitude. The VLF signals stuttered. The recovery took an hour. All of this from an event that had traveled across half the galaxy. Now imagine the same flare but closer. Imagine it at 10,000 light-years. The intensity would be 25 times greater. Imagine it at 1,000 light-years. The intensity would be 2,500 times greater. Imagine it at 100 light-years, or 10. According to Melott's calculations, a Magnetar flare of SGR 1806-20's magnitude would cause serious damage to a planet's atmosphere if it occurred within about 6 light-years. At that distance, the pulse of high-energy radiation would interact with the atmosphere in ways that go far beyond temporary ionization. It would strip electrons from molecules, break chemical bonds, set off cascades of reactions in the upper atmosphere that would take far longer than an hour to resolve. At 10 light-years, the situation becomes existential. A similar blast at 10 light-years would destroy the ozone layer, not damage it, not thin it, not create a temporary hole like the ones we worried about in the 1980s. Destroy it. The ozone that protects every living thing on this planet from the harshest ultraviolet radiation would be stripped away, and the recovery, if recovery were possible, would take years, perhaps decades. At 1,000 light-years, the risks diminish substantially, though they do not disappear. Detection would still be possible, effects on the upper atmosphere would still be measurable, but the intensity would have dropped enough that the biological consequences would be survivable, at least in the immediate term. The threshold then lies somewhere between. Somewhere in that range from 10 light-years to 1,000, there is a zone where a Magnetar flare transitions from a scientific curiosity to a regional hazard, to a global catastrophe, to an extinction event. The exact boundaries depend on factors we cannot fully control or predict. The precise energy of the flare, the orientation of the beam, the state of our atmosphere at the moment of impact. But the general shape of the danger zone is clear. It is measured in light-years, and it is not as large as we might hope. Consider what this means. We are being handed a ruler and asked to measure our own vulnerability. The distance between here and the nearest known magnetar is about 9,000 light-years. That would be 1e 1048.159 a magnetar in the constellation Carina, spinning quietly at the edge of our detection range. 9,000 light-years is well outside the immediate danger zone. A flare from that distance would be dramatic, observable, perhaps even impressive, but it would not be catastrophic. We would record it. We would study it. We would add another data point to our growing understanding of magnetar behavior, and then we would continue with our lives. But 9,000 light-years is only the nearest confirmed magnetar. It is not necessarily the nearest magnetar. The confirmed magnetars are the ones that have flared, the ones that have announced themselves, the ones that happen to do something loud during the few decades we have been capable of listening. What about the others? What about the quiescent ones, the silent ones, the ones that have not yet made themselves known? If there are hundreds of them scattered through the galaxy, then some of them must be closer than 9,000 light-years. Statistically, it would be remarkable if none of them were. The galaxy is large, but it is not uniform. We sit in a particular location, surrounded by particular stars, embedded in a particular region of the spiral arms, and somewhere in that region, in the spaces between the stars we have catalogued and the objects we have named, there may be magnetars we have not yet found. Consider the suspects we do know about. SGR 1900+14 produced its own giant flare on August 27, 1998, a date that carries its own strange symmetry with the December 27th event that came 6 years later. The August flare was intense enough to produce a marked modulation in the height of Earth's ionosphere, a 5-second periodic signal that affected long-wavelength radio transmissions. The star sits approximately 20,000 light-years away, closer than SGR 180620 but still well beyond the danger zone. Its flare lasted more than 5 minutes and was detected by multiple spacecraft, including Ulysses and Beppo-Sachs. It was a warning shot, in a sense, a demonstration that SGR 180620 was not unique, that giant flares were not once-in-a-civilization events, that the magnetars were out there, flaring, whether we were ready to receive their signals or not. And then there are the peculiar cases, the objects that do not fit neatly into our categories. SGR 0418+57729 appeared at first glance to be an unremarkable magnetar. Its magnetic field, as measured by the standard techniques, seemed almost weak by magnetar standards. Observers looked at the surface measurements and wondered if perhaps this was something different, something less dangerous, something that did not belong in the same category as the giants that had announced themselves so violently. But then came the timing anomalies, the subtle variations in the object's rotation that did not match the predictions, the hints that something was happening beneath the surface that the surface measurements could not capture. And gradually, a picture emerged of what researchers now call a hidden field magnetar, an object whose true magnetic strength is buried deep within its interior, far stronger than the surface signatures would suggest. This is a troubling category, because if there are magnetars whose magnetic fields do not announce themselves through the standard signatures, then our census is even more incomplete than we thought. We are not merely missing the quiescent ones, the ones that have not flared. We may also be missing the hidden ones, the ones that do not look like magnetars even when we do manage to observe them. They sit in our data, perhaps misclassified as ordinary neutron stars, their true nature concealed by the geometry of their fields, and when they flare, if they flare, the intensity may catch us entirely by surprise. The closest confirmed magnetar, 1E 1048.1 59327 in Carina, sits at roughly 9,000 light-years. But the closest magnetar, confirmed or not, may be much nearer. It may be half that distance. It may be a quarter. It may be sitting in a region of the galaxy we have not surveyed carefully. Or it may have been surveyed and dismissed as something else. We do not know. That is the point. We do not know. The catalogue is incomplete, the detection methods are biased toward active objects, and the hidden field phenomenon suggests that even our basic criteria for identifying magnetars may be missing a significant population. So we are left with uncertainty and with the mathematics of random orientation. If there are hundreds or thousands of magnetars in the galaxy, and if they are distributed more or less randomly through the spiral arms, then some fraction of them must be pointed toward us. Their magnetic axes, their flare beams, their emissions, some fraction must be aligned by sheer chance with the direction of our small blue planet, and some fraction of those must be closer than the ones we've found. Not because the universe is malevolent, not because anything is targeting us, but simply because the numbers are large enough that the probabilities become significant. The question, then, is not whether a magnetar could be pointed at us. The question is whether one already is. The question is whether, in the vast dark spaces between the stars, there exists an object we have not yet detected, spinning quietly, its magnetic field wound tight, its crust holding for now, but holding in a direction that, when it finally cracks, will send its burst of radiation racing toward us at the speed of light. We would not see it coming. We would not have time to prepare. The first evidence would be the evidence itself, the instrument saturating, the ionosphere flinching, the world changing in the fraction of a second it takes for light to cross the final distance. This is not speculation. This is statistics. This is the simple mathematics of large numbers and random distributions and incomplete catalogues. The universe has not promised us safety. It has not guaranteed that the nearest Magnetar will be far enough away to spare us. It has only given us the tools to ask the question, and the honesty to recognise that we do not yet know the answer. Somewhere in the darkness there are Magnetars we have not found. Some of them are pointed away from us, their flares sweeping harmlessly through empty space. But some of them, by the simple arithmetic of chance, must be pointed toward us, and they are waiting. Not with intention, not with malice, but with the patient indifference of physics. They are waiting, and we are here, and the distance between us is measured in light years that we have not yet learned to see across. The ruler is in our hands. The question is whether the measurement will arrive in time, or whether it will arrive as the event itself, written in gamma rays across a sky we thought we understood. And this is where we must pause for a moment and consider the nature of what we're trying to see. Imagine, if you will, standing alone in a vast forest at night. The trees stretch away from you in every direction, hundreds of them, thousands, their trunks rising into a darkness so complete that you cannot tell where the forest ends and the sky begins. In your hand, you hold a lantern. It casts a small circle of light around your feet, enough to see the nearest trunks, enough to make out the texture of bark and the scatter of fallen leaves. Beyond that circle, there is only blackness. You know the trees are there. You can sense them perhaps in the way the air moves, in the faint sounds of branches settling, but you cannot count them. You cannot map them. You cannot say with any certainty how many stand between you and the edge of the forest, or which direction the edge might be, or whether some of those trees are different from the others in ways that matter. Your lantern is too small, the forest is too large, and the darkness is not a failure of the forest. It is simply the natural state of a place that does not exist for your convenience. This is where we find ourselves with Magnetars. The instruments we have built, and they are remarkable instruments, sensitive and patient and far more capable than anything our grandparents could have imagined, are lanterns in a very dark forest. They illuminate what they can reach. They reveal the objects that happen to be active, that happen to be emitting, that happen to fall within their field of view at the moment they are looking. But they cannot see everything. They were never designed to see everything, and the darkness between the data points is not empty. It is full of objects we have not yet detected, some of them ordinary, some of them extraordinary, and some of them, perhaps, already pointed in our direction. The Fermi Gamma Ray Space Telescope carries an instrument called the Gamma Ray Burst Monitor. It consists of 12 sodium iodide detectors, each one sensitive to photons in the energy range from 8,000 electron volts up to 1 million electron volts, and 2 additional detectors made of bismuth germanate that extend that sensitivity up to 40 million electron volts. These detectors are arranged around the spacecraft in a careful geometry, positioned so that together they can see most of the sky at any given moment. When a burst of gamma rays arrives from somewhere in the universe, the detectors register the flash, and by comparing the signal strength across the array, scientists can estimate roughly where the burst came from. The Gamma Ray Burst Monitor has been operating since 2008, watching the sky with tireless patience, cataloguing the violent deaths of stars and the collisions of dense objects, and the occasional tantrum of a Magnetar. It is one of our best tools for detecting these events, and it has limits. The limits are not failures of engineering. They are simply the realities of building an instrument that must operate in space, with finite power, finite data bandwidth, finite sensitivity. The sodium iodide detectors can only register photons that actually strike them, which means they are blind to bursts that are too faint, too brief, or too far below their energy threshold. The localization, the ability to say where in the sky a burst originated, is good but not perfect, especially for shorter events, and the monitor can only see what it is looking at. If a burst occurs in a part of the sky that happens to be blocked by the Earth, or if the spacecraft is passing through a region of high particle background, the event may be missed entirely or recorded with such poor quality that it cannot be analysed. The Gamma Ray Burst Monitor is a magnificent lantern, but it illuminates a circle, not the whole forest. The Swift Observatory, launched in 2004, The same year the Great Flare from SGR 1806-20 swept through the solar system, carries its own detector, the Burst Alert Telescope. This is a different kind of instrument, a coded aperture telescope sensitive to hard X-rays in the range of 15 to 150,000 electron volts. Its detector area spans 5,200 square centimeters, a substantial surface designed to catch as many photons as possible from transient events. The Burst Alert Telescope is particularly good at localization. When it detects a burst, it can often pinpoint the source to within a few arc minutes, allowing other telescopes to swing around and observe the aftermath. It has been watching the sky for more than 2 decades now, detecting hundreds of gamma-ray bursts and dozens of other high-energy transients, and it too has limits. The coded aperture design means that the telescope is sensitive only within a certain field of view. Events outside that field are invisible to it. The energy range, while broad, does not extend as high as Fermi's detectors, which means some harder bursts may be partially missed. And like all instruments, it has a detection threshold, a minimum brightness below which a burst simply does not register as a burst, but as noise or as nothing at all. Then there is Integral, the International Gamma-Ray Astrophysics Laboratory, a European Space Agency mission that has been observing the high-energy sky since 2002. Integral carries several instruments designed to study gamma rays and X-rays from cosmic sources, and it has contributed to our understanding of magnetars, neutron stars, black holes, and the general violence of the universe. It too is a lantern. It too has a field of view, a sensitivity threshold, a set of energy ranges it can detect. It too is blind to what it is not looking at, and to what is too faint, and to what happens to occur during the moments when the spacecraft is occupied with other observations. These are our eyes. These are the instruments through which we watch for the flares of magnetars, the bursts of gamma rays, the signals that something violent has happened somewhere in the galaxy. They are extraordinary tools, each one the product of decades of engineering and scientific effort, each one capable of detecting events that would have been utterly invisible to observers even 50 years ago. And they are not enough. They cannot be enough. The forest is too large, and the lanterns, however bright, can only illuminate so much. Kevin Hurley, an astrophysicist who has spent much of his career studying gamma-ray bursts and high-energy transients, helps coordinate something called the Interplanetary Network, a system that uses the timing of burst arrivals at different spacecraft scattered across the solar system to triangulate the positions of events with high precision. The concept is elegant. If a burst reaches one spacecraft before another, the time difference tells you something about the direction the burst came from. By combining data from multiple spacecraft, you can narrow down the source to a small patch of sky. Hurley has spent years refining these techniques, hunting for bursts that might otherwise escape detection, trying to fill in the gaps left by any single instrument's limitations. And he understands, perhaps better than most, how much of the sky remains unseen. A quiescent magnetar, one that is not actively flaring, not emitting bursts, not doing anything to draw attention to itself, is essentially invisible to these instruments. It may be emitting a faint trickle of X-rays from its cooling surface, but that trickle could be lost in the background noise of the galaxy, or confused with emission from other sources, or simply too dim to detect at any significant distance. A quiescent magnetar within a few hundred light-years could have remained undetected through all of our existing surveys. It could be there, right now, spinning quietly in the darkness, its magnetic field wound tight, its crust intact for the moment, and we would have no way of knowing. Our lanterns would not reach it. Our instruments would not see it. It would exist in the darkness between the data points, real and present, and utterly unknown. This is not a comfortable thought. It is not meant to be. The darkness between the data points is not an abstraction. It is a physical reality, a region of space filled with objects we have not detected, some of them harmless, some of them less so. When we talk about the catalogue of known magnetars, the 30 or so confirmed objects, the additional candidates awaiting confirmation, we are talking about the trees within the circle of our lantern. We are not talking about the forest. The forest is larger. The forest contains objects we have not seen, in numbers we can only estimate, at distances we can only guess. And some of those objects, by the simple mathematics of random orientation, must be pointed toward us. Consider what we know. The Great Flare of December 27, 2004 released as much energy in 0.2 of a second as the Sun produces in 250,000 years. The total isotropic energy was measured at approximately 2 × 10 to the 46th power ergs, a number so large that it resists intuition, a number that belongs to the vocabulary of stellar explosions and cosmic catastrophes, not to the brief tantrum of a single compact object. This was the third giant flare ever recorded from a magnetar, and it was roughly 100 times more energetic than either of the two that came before. It was detected by instruments around the Earth and in orbit, its signature unmistakable, its effects measurable in the ionosphere. The CHAMP satellite, designed to study Earth's magnetic field, recorded a modulated signal with a period of 7.5 seconds. The rotation rate of the magnetar itself, imprinted on the pulse of radiation that had travelled 50,000 light-years to reach us. The Demeter satellite, designed to study electromagnetic disturbances in Earth's environment, detected the flare through its energetic ion counters. The event was global, the event was undeniable, and the event came from an object that had been known for only a few years before it flared, an object that had given relatively little warning of its violent potential. This is the nature of the threat. It is not that magnetars are malevolent. It is not that the universe is out to get us. It is simply that the forest is dark, the lanterns are small, and the objects we have not detected are under no obligation to announce themselves before they act. The instruments we have built are designed to catch flares after they happen, to record the evidence of violence that has already occurred. They are not designed to predict which quiescent object will become active, or when or how violently. They are reactive tools, not predictive ones. And in the case of a magnetar flare, the warning time is effectively zero. The radiation travels at the speed of light. The event and the evidence of the event arrive simultaneously. By the time we see the flash has already reached us. So we are left to contemplate the darkness. We are left to acknowledge that our surveys, however comprehensive they may seem, are incomplete by design. The Fermi gamma-ray burst monitor, with its 12 sodium iodide detectors and its 2 bismuth germanate detectors, is blind to quiescent objects that do not emit bursts. The Swift Burst Alert Telescope, with its 5,200 square centimeters of detector area and its coded aperture design, cannot see beyond its field of view or below its sensitivity threshold. Integral, with its decades of observations and its contributions to high-energy astrophysics, is watching only the portions of the sky it happens to be pointed at, in the energy ranges it happens to be sensitive to. Together, these instruments form a network, a system, a coordinated effort to watch the violent universe, and together they leave gaps. They must leave gaps. The forest is too large for any lantern to illuminate completely. This is not a criticism of the scientists who build and operate these instruments. It is simply a statement of physical reality. Detection has limits. Sensitivity has thresholds. Fields of view have edges. And the objects that fall outside those limits, below those thresholds, beyond those edges, they continue to exist whether we can see them or not. A magnetar within a few hundred light years, spinning quietly, waiting for its crust to crack. It would be invisible to our current capabilities. It would be a tree in the darkness, unknown and unseen until the moment it flared. And then, if it were close enough, we would learn of its existence in the worst possible way. The mood shifts here, from the clinical language of instruments and energy ranges to something deeper, something more personal. We have been speaking of detection thresholds and duty cycles and localization uncertainties. But what we are really speaking of is the darkness itself, the darkness between the stars, the darkness between the data points, the darkness that surrounds us at all times, filled with objects we have not catalogued, events we have not witnessed, threats we have not assessed. We live in a universe that does not exist for our convenience. It does not arrange itself to be seen. It does not time its violence to coincide with our observations. It simply is, vast and indifferent, and we are small creatures with small lanterns, trying to map a forest that extends beyond the reach of any light we can carry, and yet there is a strange comfort in this, if you are willing to look for it. The darkness is not malevolent. The universe is not hunting us. The magnetars that spin unseen in the depths of the galaxy are not aiming at us with intention. They are simply there, products of stellar evolution and gravitational collapse. Their orientations determined by the random tumbling of their progenitor stars, their flares triggered by the slow accumulation of stress in their crystalline crusts. If one of them is pointed toward us, it is pointed toward us by chance, not by design, and chance is not personal. Chance does not care. Chance is simply the mathematics of large numbers and random distributions, playing out across a galaxy that contains hundreds of billions of stars and an unknown number of their most violent remnants. But comfort does not erase risk. And the risk, as we now turn to consider, is not merely theoretical, it is historical. It has happened before, not in recorded human history, but in the deeper history of life on Earth, written in the fossil record and the chemistry of ancient rocks. The universe has reached out before, in ways that shaped the course of evolution on this planet, and the evidence suggests that it may have done so with precisely the kind of violence we have been contemplating. 445 million years ago, give or take a few million years in either direction, the Earth was a different world. The continents were arranged differently, clustered mostly in the southern hemisphere, surrounded by vast oceans teeming with life. But that life was almost entirely marine. The land was barren, or nearly so, perhaps some hardy algae clinging to rocks near the water's edge, perhaps some primitive lichens beginning their slow colonization of the continents, but nothing that would be recognizable as a plant or an animal in the modern sense. The great drama of life was playing out in the oceans, where trilobites crawled across the seafloor, where brachiopods filtered nutrients from the water, where graptolites drifted in vast colonial chains through the upper layers of the sea. It was a world of shells and segments, of creatures that had evolved over hundreds of millions of years to fill the ecological niches available in a warm, shallow, sunlit ocean. And then, over a geologically brief interval, a catastrophe struck. The late Ordovician mass extinction, one of the 5 great extinction events in the history of complex life, swept through the oceans and eliminated between 49 and 60% of all marine genera. By some estimates, nearly 85% of marine species vanished during this crisis. The trilobites, which had dominated the seafloor for millions of years, were devastated. The graptolites were nearly wiped out. Entire families of brachiopods disappeared, leaving gaps in the fossil record that would not be filled for millions of years. It was, in its way, a rehearsal for the even greater catastrophe that would come at the end of the Permian period, some 200 million years later. But for the creatures that lived through it, or failed to live through it, the Ordovician extinction was plenty catastrophic enough. For a long time, the cause of this extinction was attributed to climate. The evidence showed that the late Ordovician was marked by intense rapid cooling, a glaciation event that lowered sea levels, disrupted ocean circulation, and stressed the warm water ecosystems that had flourished during the preceding period. And climate change remains a significant factor in most analyses of the extinction. But in more recent decades, researchers have begun to ask whether something else might have been involved as well, whether the cooling itself might have been triggered or amplified by an event from beyond the Earth. The gamma-ray burst hypothesis was developed by a group of astrophysicists including Brian Fields of the University of Illinois and John Ellis, working with collaborators who brought together expertise in high-energy astrophysics, atmospheric chemistry and paleontology. The idea is straightforward in principle, though complex in its details. A gamma-ray burst, or a giant flare from a magnetar, which produces similar radiation, arriving at Earth from a sufficiently close source, would deposit enormous amounts of energy in the upper atmosphere. That energy would drive chemical reactions that would destroy ozone, the molecular shield that protects the surface of the planet from the sun's ultraviolet radiation. With the ozone layer depleted or destroyed, ultraviolet light would reach the surface at levels far higher than normal, with devastating effects on life. The primary target would be phytoplankton, the tiny photosynthetic organisms that form the base of the marine food chain. Phytoplankton are exquisitely sensitive to ultraviolet radiation. Their DNA is damaged by UV exposure, their photosynthetic machinery is disrupted, their reproduction is impaired. In the modern ocean, they are protected by the ozone layer, which absorbs most of the harmful UV before it reaches the surface. But strip away that protection, even temporarily, and the phytoplankton would suffer massive die-offs. And when the phytoplankton die, everything that eats them begins to starve. The zooplankton that graze on phytoplankton would decline. The small fish that eat zooplankton would follow. The larger predators, the filter feeders, the entire complex web of marine life that depends ultimately on the productivity of photosynthesis at the base. All of it would be stressed, disrupted, diminished. The collapse would cascade upward through the food chain, from the microscopic to the macroscopic, from the surface waters to the depths. This is the mechanism that Fields, Ellis, and their collaborators proposed. A nearby gamma-ray burst, or a Magnetar flare, which produces gamma radiation in a similar energy range, could have triggered the ozone depletion that stressed the Ordovician marine ecosystem. The ultraviolet damage would have weakened the base of the food chain, making the entire system more vulnerable to the climate disruptions that followed. The glaciation itself might even have been triggered or amplified by the event, as changes in atmospheric chemistry altered the planet's heat balance. The extinction, in this model, was not caused by a single factor, but by a cascade of factors, each one making the others worse, each one driven ultimately by a pulse of radiation from a dying star tens or hundreds of light years away. How close would the source need to be? The calculations suggest that a gamma ray burst within a few thousand light years could cause significant ozone depletion. A Magnetar flare, with its somewhat different energy spectrum and shorter duration, might need to be even closer to produce similar effects. The details depend on the energy of the event, the orientation of the beam, the state of the Earth's atmosphere at the time. But the basic conclusion is clear. The Earth is not immune to events that originate in deep space. The galaxy is not a passive backdrop to the story of life on this planet. It is an active participant, capable of reaching out across light years to shape the conditions under which life evolves, thrives, or perishes. The late Ordovician extinction was global. It affected organisms across the planet, in all the major ocean basins, at all depths and latitudes. The pattern of extinction and survival shows some interesting features. Organisms that lived in shallower water, closer to the surface, seem to have suffered more than those that lived in deeper water, more shielded from direct sunlight. This is consistent with the ultraviolet hypothesis, though it is not definitive proof. Other factors could produce similar patterns, but the consistency is suggestive. It fits the model. It hints at a mechanism that comes from above, from the sky, from beyond the protective blanket of water and atmosphere that usually shields life from the violence of the cosmos. A dangerously close gamma-ray burst or Magnetar flare, according to the statistical models, should occur on average 2 or more times per billion years. The Earth is roughly 4.5 billion years old. Life has existed here for most of that time. The numbers suggest that the planet has been bathed in deadly radiation multiple times over its history, not every few million years, not with the frequency of asteroid impacts or volcanic eruptions, but often enough that it cannot be ignored. Often enough that it leaves traces in the fossil record. Often enough that when we contemplate the future, we must include it in our calculations. This is what shifts the conversation from speculation to history. The gamma-ray burst hypothesis for the Ordovician extinction is not proven. It may never be proven, given the difficulty of finding direct evidence for an event that occurred nearly 500 million years ago. But it is plausible. It is consistent with what we know about the effects of high-energy radiation on planetary atmospheres and ecosystems. And it transforms the threat we have been discussing from an abstract possibility to a concrete precedent. The universe has reached out before. It has touched the Earth before. It has shaped the history of life before. The magnetars spinning unseen in the darkness of the galaxy are not hypothetical dangers. They are part of a category of phenomena that has, in all likelihood, already influenced the course of evolution on this planet. Spare a thought, then, for the trilobites. They did not know what hit them. They had no instruments to detect gamma rays, no theories to explain ozone depletion, no concept of magnetars or neutron stars or the violent deaths of massive suns. They simply lived their lives in the warm Ordovician seas, filtering food from the water, crawling across the muddy bottom, doing whatever it is that trilobites did in their hundreds of millions of years of existence. And then the sky turned hostile. The sunlight that had always nourished the phytoplankton began to kill them instead. The food chains collapsed, the oceans emptied, and the trilobites, most of them, died. They did not understand. They could not understand. But we can. We have the tools to detect the radiation, the theories to explain the mechanism, the instruments to watch the sky for signs of danger. We know what magnetars are. We know what they can do. We know that the fossil record contains at least one mass extinction that may have been triggered or amplified by a burst of radiation from deep space. We are not trilobites, we have lanterns, and yet our lanterns are small. The forest is dark, the objects we have not detected continue to spin, unseen, in the spaces between the stars. The question is not whether such events have happened. The evidence suggests they have. The question is not whether they could happen again. The physics says they will eventually on timescales that are long by human standards but short by geological ones. The question is whether we will see it coming. The question is whether our lanterns will illuminate the right tree at the right moment, or whether the darkness will deliver its message without warning, in gamma rays and ultraviolet light, in the language of mass extinction and ecological collapse. The Ordovician oceans did not recover quickly. It took millions of years for the diversity of marine life to return to pre-extinction levels. New species evolved to fill the empty niches. New forms of trilobites, reduced in diversity but still present, continued to crawl across the seafloor. New brachiopods, new graptolites, new communities of organisms adapted to the changed conditions. Life persisted. Life always persists, on some level, in some form. But the world that emerged from the extinction was not the world that had existed before. It was a different world, shaped by the catastrophe, marked by the loss of what had come before. And so we return, once more, to the Magnetar we have come to know best. SGR 1806-20, spinning in the darkness of the Scutum Centaurus arm, 50,000 light-years from the bed where you now rest. We have spoken of what it did on December 27, 2004. We have traced the ripples of that event through the instruments that recorded it, through the ionosphere that felt it, through the theoretical models that attempted to explain it. But there is a part of the story we have not yet examined closely, a detail that transforms the event from remarkable to unsettling in a way that lingers. The giant flare did not arrive without warning, not entirely. In the months leading up to that December night, the Magnetar had been restless. It had been speaking in its way, in a language of smaller bursts and subtle variations that the instruments were trained to hear. Crissa Cuveliotu and her colleagues had been watching. They had been monitoring the source with the Rossi X-ray timing explorer, tracking its pulse frequency, noting the erratic variations in its spin-down rate. The Magnetar was not silent before it screamed. It was murmuring. It was building towards something. This is one of the strange gifts of the 2004 event. One of the reasons it occupies such a central place in our understanding of magnetars. We have data from before, during and after. We can see the approach, the climax, and the aftermath. We can study the correlation between pulsed flux and torque in the months surrounding the flare, the way the object's behavior changed as the stress accumulated in its crust as the magnetic field lines twisted and strained toward the breaking point. Peter Woods, Crissa Cuveliotu, and others had been publishing on SGR 1806-20's activity throughout that year. They knew something was happening. They could see the restlessness in the data. What they could not know was how large the release would be when it finally came. What they could not predict was that December would bring the brightest gamma-ray flare ever recorded, a burst of energy that would saturate instruments designed to measure the most violent events in the cosmos. The flare itself was not a single uniform pulse. It had structure. It had phases. In the first fraction of a second, there was a relatively soft, fast peak, a precursor that arrived just milliseconds before the main event. And then the main peak came, and it overwhelmed everything. The instrument saturated. The detectors, designed to measure gamma rays from across the universe, found themselves blinded by a source that was, in cosmic terms, practically next door. The saturation lasted approximately half a second, though different instruments recorded slightly different durations depending on their sensitivity and design. Half a second. In that half second, the Magnetar released more energy than the Sun produces in 150,000 years. The radiation spread outward at the speed of light, a sphere of gamma rays expanding into the galaxy, washing over everything in its path. And here is the detail that matters most, the one that should settle into your thoughts as you drift towards sleep. The flare was directional, not perfectly directional, not like a laser, but concentrated. The initial hard spike, the most energetic fraction of that already extraordinary release, was beamed. It swept through space like the light from a lighthouse, rotating with the Magnetar's spin, painting a path across the cosmos. And Earth was not in that path. We were not in the direct beam. We were in the scatter. The radiation that ionized our ionosphere, that caused the instruments to saturate, that produced effects measurable from Hawaii to Antarctica, that was the spillover. That was what leaked around the edges. That was the light that missed us and still managed to reach us, attenuated by geometry, softened by the simple fact that we were not where the beam was pointing when it fired. Consider what this means. The event that we have been discussing, the flare that altered our upper atmosphere from 50,000 light-years away, the burst that stands as the brightest gamma-ray flash ever detected at Earth, that was not the full force of what SGR 180620 released. That was a glancing blow. That was the edge of the weapon, not its point. If the Magnetar had been oriented differently, if its rotation had placed Earth in the direct path of that initial hard spike, the story we are telling would be different. The numbers would be different. The effects would be different. We speak of the ionosphere recovering in 60 minutes, of the D-layer electron density increasing 100-fold and then slowly returning to normal. But those are the numbers for what actually happened, for the geometry that actually existed on December 27th, 2004. They are not the numbers for what could have happened. They are not the numbers for what will happen, eventually, when some magnetar somewhere in the galaxy happens to be pointed in precisely the wrong direction, at precisely the wrong moment. The lighthouse does not care what lies in its path. It simply turns. The beam sweeps across the ocean, illuminating whatever happens to be there when the light arrives. A ship in the wrong place sees the full glare. A ship a few degrees to the side sees only the glow. SGR 180620 was a lighthouse 50,000 light-years away, and we were the ship a few degrees to the side. We saw the glow. We felt the glow. The glow was enough to ionize the upper atmosphere of our planet. And we were not even in the beam. This is the near miss that the data reveals, the close call that hides inside the event we have been examining. It is not a speculation. It is a consequence of the physics. Magnetar flares are not isotropic. They do not radiate equally in all directions. The initial spike is concentrated, beamed by the geometry of the magnetic field and the dynamics of the energy release, and the beam rotates with the star. It sweeps. It paints a circle across the sky with every rotation, and whatever lies along that circle receives the full force of what the Magnetar has to offer. We were not along that circle. We were nearby. We were close enough to feel the edge, to record the scatter, to have our ionosphere disturbed by radiation that had travelled for 42,000 years before reaching us. But we were not in the beam. The next time may be different. The next Magnetar, the next giant flare, the next lighthouse sweeping its beam across the cosmos. There is no reason to believe we will be so fortunate again. There is no mechanism that protects us, no physical law that keeps the beams pointed away from Earth. It is simply geometry, simply chance, simply the rotation of objects we cannot see and cannot predict. And so, we file this away, this detail about December 2004, this quiet revelation that the worst Magnetar event ever recorded at Earth was not even the worst it could have been. The beam missed, the scatter hit, and still the scatter was enough to alter our atmosphere, to saturate our instruments, to demonstrate that the universe can reach out and touch us from distances that dwarf the imagination. Let us sit for a moment with a different number. Let us think about what happens when the distance shrinks. Not 50,000 light-years, not the far side of the galaxy where SGR 180620 spins in its lonely vigil. Let us think about 10,000 light-years. The distance of nearby stellar populations, the distance of the Orion Arm, the spiral structure in which our own sun is embedded. 10,000 light-years is still an almost incomprehensible gulf, still a span that would take our fastest spacecraft tens of millions of years to cross. But it is also 1/5 the distance to SGR 180620, and in the arithmetic of radiation, in the cold mathematics of the inverse square law, 1/5 the distance means 25 times the intensity. 1/5 the distance means the energy that reached Earth from SGR 1806 to 20 would be multiplied by a factor of 25 if the same flare occurred from a Magnetar at 10,000 light-years. But let us be conservative. Let us speak of half the distance, not 1/5. Let us imagine a Magnetar at 25,000 light-years, roughly half the distance to SGR 180620. Even at half the distance, the intensity quadruples. The radiation that ionized our upper atmosphere, that disturbed the D-layer, that altered radio propagation across the Pacific, that radiation would arrive 4 times stronger, The effects would scale accordingly. But 10,000 light-years is the number that atmospheric chemists have modelled, the distance at which the consequences shift from interesting to alarming, from measurable to consequential. At 10,000 light-years, a giant flare equivalent to SGR 1806-20 would not merely ionise the upper atmosphere, it would begin to damage it. The ozone layer, that thin shield of triatomic oxygen that protects the surface from the sun's ultraviolet radiation, would begin to break down. The gamma rays would trigger a cascade of chemical reactions in the stratosphere, splitting oxygen molecules, forming nitrogen oxides, catalysing the destruction of ozone on a scale that would take years to recover. The models are not precise. The literature on magnetar flares at arbitrary distances remains sparse. The calculations depend on assumptions about flare spectra and atmospheric chemistry that carry significant uncertainties. But the direction is clear. The ozone column would deplete, 35% perhaps more. A third of the shield gone. Think about what a 35% reduction in stratospheric ozone means at the surface. The ultraviolet radiation that reaches your skin, the radiation that causes sunburn and skin cancer and cataracts, the radiation that damages DNA and kills microorganisms and bleaches coral. That radiation is filtered by the ozone layer. A 50% reduction in ozone, according to the atmospheric models, would increase UV intensity by a factor of 2 at 305 nanometers, and by a factor of 50 at 295 nanometers. The shorter wavelengths, the more biologically active wavelengths, the wavelengths that do the most damage to living tissue, those are the ones that increase most dramatically when the ozone thins. A 35% depletion would not produce effects quite as severe, but it would still be profound. It would still be noticeable. It would still be dangerous. Prolonged outdoor exposure would become hazardous within weeks. Not immediately, not in the flash of the flare itself. The gamma rays would be absorbed high in the atmosphere, and the surface would be shielded from the initial burst. But the ozone depletion would persist. The chemical changes in the stratosphere would continue, and the sunlight that reached the ground in the days and weeks and months that followed would be subtly different, richer in ultraviolet, harsher on exposed skin. The UV index, that number the weather services report alongside temperature and precipitation, the number that tells you whether to wear sunscreen, that number would climb. It would climb and stay high. It would climb high enough that the warnings we currently reserve for summer afternoons at tropical beaches would apply to ordinary mornings in temperate latitudes. This is not the apocalypse. This is not the end of civilization. It is something more insidious, something slower, something that would unfold over months and years rather than hours and days. The ozone layer would eventually recover, as it does after volcanic eruptions and solar storms and the accumulated damage of chlorofluorocarbons. But the recovery would take time. Years, perhaps decades, depending on the severity of the initial depletion. And during that time, the world would be different. The sunlight would be different. The risk calculus of stepping outside would be different. We would adapt, as humans always adapt. We would wear more sunscreen, stay indoors during peak hours, modify our behaviour to account for the changed conditions. But we would be living under a wounded sky, a sky that had been damaged by an event from 10,000 light-years away, an event we never saw coming, an event that arrived at the speed of light from a source we had never detected. And there is another dimension to consider, one that operates on a faster timescale. The ionosphere, that electrically charged layer of the upper atmosphere, is not merely a scientific curiosity. It is infrastructure. It is the medium through which radio waves propagate, the layer that reflects certain frequencies back to Earth and allows communication over the horizon. It is the region through which GPS signals pass, where their timing is subtly affected by the density and distribution of free electrons. The 2004 flare from SGR 1806-20, from 50,000 light-years away, ionized the D layer for 5 minutes to a depth greater than even the largest solar flares produce. Navigation and communication systems rely on ionospheric stability. They rely on the electron density being predictable, being stable, being within the parameters that the engineers designed for. A magnetar flare at 10,000 light-years would not merely exceed those parameters, it would obliterate them. Picture, if you can, the moment of the flare. Gamma rays arriving at the speed of light, no warning, no precursor, no time to prepare. The ionosphere lighting up like a fluorescent bulb, the electron density spiking to levels never before recorded, The radio blackouts spreading across the hemisphere facing the source. GPS signals delayed, distorted, unreliable. Aircraft navigation systems reporting anomalies. Ships at sea losing their satellite fixes. The global positioning infrastructure, the invisible grid that guides everything from container ships to delivery drones to the phone in your pocket, suddenly uncertain, suddenly untrustworthy. It would last minutes, perhaps hours, depending on the intensity and duration of the flare, and then it would pass, and the ionosphere would begin to recover, and the systems would recalibrate, and the world would return to something like normal. But for those minutes, for those hours, the thin shell of technology that wraps the planet would flicker. The infrastructure would bend. This is not speculation about what might happen in some distant future. This is extrapolation from what we have already observed, from the data we already have, from the flare we have already studied. The 2004 event provides the baseline. The physics provides the scaling laws. The conclusion is arithmetic, not imagination. A Magnetar flare at 10,000 light-years would be more intense than what we experienced from SGR 180620. The effects would be correspondingly more severe. The ionospheric disruption would be longer and deeper. The ozone depletion would be measurable and lasting. The world would notice. The world would feel it. And there would be no warning, no advance notice, no time to prepare. The radiation travels at the speed of light. It arrives the moment we see it. There is no gap between detection and impact. There is one more thing worth understanding about magnetars, one more aspect of their nature that makes the threat we have been discussing so difficult to assess. It concerns time. It concerns the long, slow rhythms of these objects, the cycles of activity and quiescence that govern their behaviour over spans that dwarf human history. A magnetar does not burn steadily like a candle. It does not fade smoothly like a dying ember. It flickers, it bursts, it goes quiet, and the quiet periods can last a very long time. After an active burst period, after a sequence of flares and starquakes and electromagnetic outbursts, the Magnetar's surface crust relaxes. The stress that had accumulated, the tension in the magnetic field lines, the energy stored in the twisted geometry of the field, it has been released. The object settles. The crust cools. The field begins a slow process of decay, a gradual weakening that unfolds over timescales measured in thousands and millions of years. The magnetar dims. It becomes harder to see. The X-ray emission that betrayed its presence, the signature that allowed our instruments to detect it, fades to levels below the threshold of our telescopes. The object is still there. It is still spinning. It is still carrying its enormous magnetic field. But it has become invisible to us. It has entered a quiescent phase. The Magnetar XTE JA-1810-197 offers a window into these rhythms. It is one of the objects for which we have been able to observe the longest quiescent period following an outburst, approximately 11 years of relative silence after a period of detectable activity. 11 years is a long time by human standards, long enough for a child born during the outburst to reach middle school by the time the quietude ended. But 11 years is nothing by Magnetar standards. It is a heartbeat. It is a pause between breaths. The theoretical model suggests that magnetars can remain quiescent for far longer, centuries, millennia, perhaps longer still. The emission strength and the physical parameters of these objects co-evolve on timescales of approximately 1 million years. The magnetic field slowly decays through ohmic dissipation, through conduction and diffusion in the dense matter of the neutron star's interior. The energy that drives the burst gradually depletes. The object grows quieter, fainter, harder to see. And this is where the darkness of the situation becomes most apparent. This is where the epistemological problem we have been circling throughout this story reveals its sharpest edge. A quiescent magnetar is, for all practical purposes, undetectable with current technology. Our instruments are designed to see activity, X-ray bursts, gamma-ray flares, the electromagnetic signatures of a magnetar in its restless phase. When a magnetar goes quiet, when it settles into a long dormancy between active periods, it becomes a dark object in a dark sky. It emits nothing we can see. It betrays nothing we can measure. It simply spins, silent and invisible, carrying its enormous magnetic field through the void, waiting for the next phase of activity, the next accumulation of stress, the next starquake that will crack the crust and release another flare. Nandareya and her collaborators have studied the follow-up observations from the 2004 SGR 1806-20 event, tracking the Magnetar's behaviour in the years that followed. The work illuminates the complex relationship between magnetic field evolution and observable emission, the way these objects change over time, the way their detectability varies with their internal state. But the fundamental problem remains. We can study the magnetars we have found. We can model their behaviour, track their variations, predict their evolution on theoretical grounds. What we cannot do is find the magnetars that are not currently active. What we cannot do is see the ones that have gone quiet. The silence of a magnetar is not evidence of safety. This is perhaps the most unsettling truth that emerges from the physics, the observation that should accompany you as you settle deeper into your pillow. When we look at the sky and see nothing, when our instruments scan the galaxy and detect no magnetar in a particular region of space, we're not learning that the region is safe. We're not confirming that no magnetar exists there. We're simply learning that if a magnetar does exist there, it is not currently active. It is not currently emitting the radiation that would reveal its presence. It is quiet. It is dark. It is waiting. The theoretical estimates suggest that hundreds, perhaps thousands of magnetars exist in the Milky Way. We have found fewer than 30. The discrepancy is explained by the quiescent phases, by the long dark intervals between periods of activity, by the fundamental bias in our detection methods toward objects that are currently doing something visible. The majority of magnetars in the galaxy are at any given moment invisible to us. They are spinning in the darkness, their magnetic fields slowly decaying, their crusts slowly accumulating the stress that will eventually trigger the next starquake, the next burst, the next flare, and we have no way of knowing where they are. We have no way of knowing how close the nearest one might be. We have no way of knowing whether one is pointed at us right now, dark and silent, counting down to its next release. This is the clockwork we cannot see. This is the mechanism that operates beyond the reach of our instruments, beyond the scope of our surveys, beyond the boundaries of what we can currently observe. The magnetars we have catalogued are the ones that happen to be active during the brief window of time that we have been watching. The ones that were quiet during that window, the ones that finished their last active phase before we built our X-ray telescopes and gamma-ray observatories, the ones that will not begin their next active phase until long after our instruments have fallen silent. Those magnetars are invisible to us. They are part of a population we know must exist but cannot directly observe. They are the dark majority. And among that dark majority, somewhere in the spiral arms of the galaxy, there may be objects closer than any we have yet detected. Objects that lie within 10,000 light-years, within 5,000, within the range where a giant flare would do real damage to our atmosphere and our infrastructure. Objects that are currently quiescent, currently invisible, currently unknowable. Objects that will, eventually on some timescale we cannot predict, become active again. Objects that will release their accumulated energy in bursts and flares, in the violent electromagnetic signatures that we have learned to recognize and fear. And when they do, the radiation will travel outward at the speed of a light, crossing the gulf between the source and the Earth in a journey that takes thousands or tens of thousands of years, arriving without warning, arriving without announcement, arriving at the same moment we first detect the flare that produced it. The absence of a signal is not the absence of a threat. The darkness of the sky is not the safety of the Earth. The instruments we have built can see only what is currently visible, and magnetars spend most of their existence invisible. This is the core of the problem, the heart of the uncertainty that we carry with us as we contemplate these objects. We do not know what is out there. We cannot know what is out there. The physics of Magnetar evolution ensures that most of them, at any given moment, are hidden from us, dormant, waiting, accumulating the energy for their next release. And so we live, as we have always lived, under a sky whose contents we do not fully understand. We build our instruments and scan the heavens and catalogue what we find, and we tell ourselves that we are making progress, that we are pushing back the darkness, that we are illuminating the corners of the cosmos where danger might lurk. And we are. We are doing all of those things. But the magnetars remind us that some corners remain dark no matter how bright our lanterns. Some objects remain hidden no matter how sensitive our detectors. Some threats remain invisible until the moment they announce themselves, and by then it is too late to prepare, too late to respond, too late to do anything but endure what comes. The clockwork turns, the silent magnetars spin, the crusts accumulate stress, the fields slowly decay. And somewhere in the galaxy, perhaps closer than we know, perhaps pointed in a direction we would prefer it not to point, a magnetar waits in its long dormancy, dark and patient, counting down to an awakening we will not see coming. The light from that awakening is already travelling toward us, or it will be soon, or it will be in 1,000 years or 10,000. We do not know, we cannot know. We can only watch and wait, and hope that when the next great flare occurs we will be fortunate enough to be a few degrees to the side once more, in the scatter rather than the beam, feeling the edge of the weapon rather than its point. The lighthouse turns, the beam sweeps, and the ships on the dark ocean have no way of knowing where the light will fall. And so we return, one final time, to where we began. December 27th, 2004. A Monday. The last full week of the year, that strange interstitial time when calendars seem to hold their breath. In most of the world, the day passed like any other late December day. Families gathered around tables laden with leftovers, children played with new toys, travellers made their way home through airports and train stations, the ordinary business of life continuing in its ordinary rhythms. The sun rose and set. The tides pulled at the shores. The earth turned on its axis, as it had for 4.5 billion years, carrying its cargo of life through the darkness between the stars. And at 21:30:26.5, universal time, late evening in Europe, afternoon in the Americas, the small hours of the following morning in the Far East, something arrived. It had been travelling for 50,000 years. It had left its source when the first modern humans were just beginning to spread across the African continent, when the great ice sheet still covered much of Europe and North America, when the world was a colder and more dangerous place than it is today. It had crossed the vast emptiness of interstellar space, threading its way through the spiral arms of the galaxy, passing stars and planets and moons and asteroids, passing through regions of dust and gas, passing through the cold void where nothing exists but the faint background radiation left over from the birth of the universe itself. For 50 millennia it had travelled, and in all that time it had encountered nothing that could stop it, nothing that could slow it, nothing that could deflect it from its path. It moved at the speed of light because it was light. Gamma rays, X-rays, the highest energy photons the universe can produce, born in the catastrophic magnetic reconnection event that occurred when the crust of a neutron star cracked open and released its accumulated tension in a single, devastating pulse. The Magnetar SGR 1806-20, sitting in the Scutum Centaurus arm of the Milky Way, had been building toward this moment for years. Its magnetic field, twisted and stressed by the slow rotation of the star, had been accumulating energy in the form of magnetic tension, the way a rubber band accumulates energy when you twist it between your fingers. And on that December day, the tension finally exceeded what the crust could bear. The crystalline surface of the neutron star, a lattice of exotic matter held together by forces we barely understand, fractured, and in that fracturing, in that sudden release of magnetic energy, the magnetar produced the brightest flash of electromagnetic radiation ever recorded from outside our solar system. The initial spike lasted 0.2 of a second, 200 milliseconds, the time it takes to blink, the time it takes a hummingbird's wing to complete a single downstroke, the time it takes sound to travel about 70 meters through air. In that eye blink of cosmic time, SGR 1806-20 released more energy than our Sun produces in 250,000 years. The number is almost meaningless to the human mind. We cannot truly comprehend what it means for an object smaller than a city to produce that much energy in that little time. But perhaps we can understand the consequences. The gamma rays arrived at Earth and immediately began interacting with the upper atmosphere. The photons, each one carrying enormous energy, slammed into the atoms and molecules of the ionosphere and knocked electrons free. The D layer of the ionosphere, that region between 60 and 90 kilometers above the Earth's surface where long wavelength radio signals are absorbed and reflected, experienced a sudden dramatic increase in electron density. The ionization was measurable, it was significant. It was, in the language of atmospheric physics, anomalous. At monitoring stations scattered across the globe, instruments designed to track very low-frequency radio signals registered the disturbance. In the Far East, along the monitoring paths that connected transmitters and receivers in Petropavlovsk, Kamchatsky and other stations, the amplitude and phase of VLF signals shifted abruptly. The measurements showed what scientists later confirmed. The radiation from a Magnetar 50,000 light-years away had altered the electrical properties of our planet's upper atmosphere. The effect was temporary. The ionosphere began recovering within minutes, but it was real, it was measurable, and it was unprecedented. No event from beyond our solar system had ever been observed to directly affect the Earth's atmosphere before. This was not a theoretical calculation, not a model, not a prediction. This was data. This was recorded. This was, in the most literal sense possible, contact between our world and the violent heart of a dying star half a galaxy away. The initial spike was only the beginning. After that first devastating pulse, the Magnetar continued to radiate, its emission pulsating with the 7.5-second rotation period of the neutron star itself. The tail of the flare lasted nearly 400 seconds, more than 6 minutes of sustained pulsing radiation, the Magnetar's magnetic field ringing like a struck bell, slowly dissipating its energy into the void. Some sources recorded the hard X-ray tail persisting for 380 seconds. Others measured variations lasting closer to 600 seconds. The discrepancy in the literature reflects the difficulty of measuring an event that saturated nearly every detector designed to observe it. The instruments we had built to study the high-energy universe were not built to handle something this bright. They were overwhelmed, their carefully calibrated sensors driven into saturation, their data contaminated by the very intensity they were trying to measure. 7 days after the flare, radio telescopes detected something new, a transient radio source catalogued as VLA J1 Dinon appeared in the region of the sky where SGR 1806 and 20 sits. The radio emission was the afterglow of the flare, the electromagnetic echo of the catastrophic event, produced as the expanding cloud of charged particles ejected by the Magnetar interacted with the surrounding medium. The radio afterglow was detected by observatories on 3 continents, a global network of telescopes turning their attention to this tiny patch of sky where something extraordinary had just occurred. And at monitoring stations in Antarctica, in the quiet laboratories where researchers track the subtle variations in very low-frequency signals propagating through the Earth's atmosphere, the ionospheric signature of the flare was logged and recorded. The data showed the spike, the recovery, the slow return to normal conditions. The data told the story of an atmosphere that had been touched by something impossibly distant and impossibly powerful and had survived. This is what we knew. In the days and weeks after December 27, 2004, this is what the instruments told us. This is what the data revealed. But what we understand now, with everything we have learned in the years since, is something larger, something more sobering. The flare from SGR 1806-20 was not aimed at Earth. The initial spike, that devastating 200 millisecond pulse that saturated our detectors and ionized our upper atmosphere, was produced by a beamed emission, a concentrated jet of radiation that shot outward from the magnetic poles of the neutron star. That beam missed us. We were not in the direct line of fire. What we received was the scattered radiation, the secondary emission, the light that spread outward in all directions after the initial pulse. We were standing to the side of the searchlight, not in front of it. We felt the edge of the weapon, not its point, and even the edge of that weapon, arriving from 50,000 light-years away, was enough to measurably alter our ionosphere. Consider what this means. Consider the scaling. Consider the mathematics of inverse squares, the brutal arithmetic of distance and intensity. If SGR 1806-20 had been 10,000 light-years away instead of 50,000, the radiation reaching Earth would have been 25 times more intense. If it had been 1,000 light-years away, the intensity would have been 2,500 times greater. If it had been 100 light-years away, still an enormous distance by human standards, still a gulf that would take our fastest spacecraft tens of thousands of years to cross. The radiation would have been 250,000 times more intense than what we actually received. And if it had been 10 light years away? If this Magnetar or one like it had been sitting in our immediate cosmic neighbourhood among the handful of stars we can see with the naked eye? The gamma-ray dose would have been comparable to a nearby supernova. The ozone layer would not have flinched. It would have failed. The stratospheric chemistry that shields all life on Earth from the sun's ultraviolet radiation would have been disrupted on a planetary scale. The effects would have lasted not minutes but months, perhaps years. The consequences would have been measured not in anomalous VLF readings, but in mass extinctions. December 27, 2004 was a near miss. Not in the sense that the radiation came close to Earth and barely passed us by. The radiation hit us directly, but in the sense that the universe, in its vast indifference, happened to place this particular violent object at a distance great enough to be survivable, and happened to orient its beam in a direction that did not include our planet. We were lucky. We were fortunate. We were the beneficiaries of geometric chance on a cosmic scale, and we did not know it was happening until it had already happened. The light arrived at the same instant we detected it. There was no warning, no announcement, no time to prepare. The radiation that ionized our upper atmosphere had been travelling toward us for 50,000 years, and we had no idea it was coming until the moment it arrived. This is the nature of electromagnetic radiation. This is the nature of threats that move at the speed of light. There is no advance notice, there is no early warning system, there is only the event itself, arriving without prelude, and the aftermath that follows. Let that settle for a moment. The brightest flash of extrasolar radiation ever recorded at Earth came and went before anyone knew to look for it. The ionosphere flinched and recovered while the world went about its business, while families finished their holiday meals and travellers made their way through airports and children played with their new toys. The universe reminded us of its violence, and most of humanity never noticed. This is not a criticism. This is simply a description of reality. We live our lives at the human scale, concerned with human timescales and human distances, and the cosmos operates at scales that dwarf everything we know. The gap between our experience and the universe's behaviour is so vast that events like the December 2004 flare can occur, events that would have been catastrophic had the geometry been slightly different, and pass almost entirely unnoticed by the species whose planet was briefly touched by their radiation. And this brings us to the question that has been building throughout everything we have discussed tonight. The question that underlies all the physics and all the statistics and all the careful calculations of distance and intensity. The question that cannot be answered with certainty, no matter how sophisticated our instruments become. What else is out there? We know that SGR 180620 is one of fewer than 30 magnetars we have confirmed in our galaxy. We know that this number represents a tiny fraction of the magnetars that actually exist. The models suggest hundreds, perhaps thousands, scattered throughout the spiral arms of the Milky Way. We know that most magnetars spend most of their existence in quiescent phases, dark and invisible to our current instruments, detectable only when they become active and begin emitting the X-rays and gamma rays that our telescopes can see. We know that the magnetars we have found represent an observational bias, a selection effect, a catalogue of the visible that says nothing about the invisible. And we know that among those invisible magnetars, the dark majority, the ones we cannot detect, there may be objects closer to Earth than any we have yet confirmed. Objects within 10,000 light years, within 5,000, within 1,000. Objects that are currently quiescent, currently dormant, currently accumulating the magnetic stress that will eventually lead to their next giant flare. Objects that may already be oriented in our direction, their magnetic poles pointed toward our corner of the galaxy, waiting for the moment when their crusts will crack and their fields will reconnect and their beams will sweep across the darkness toward us. The absence of a detection is not the absence of a threat. The silence of the sky is not the safety of the Earth. But we are not helpless, we are not entirely blind, and here, in the final movement of this long meditation on violence and distance and chance, it is worth considering what we are building, what tools we are creating to push back the darkness, even if only by a little, what lanterns we are carrying into the forest. The square-kilometre array is under construction as I speak to you tonight. In South Africa and Australia, engineers and scientists are assembling what will become the most sensitive radio telescope ever built, a vast network of antennas spread across 2 continents, working together as a single instrument capable of detecting signals that current telescopes cannot see. The first phase of the SKA will have nearly an order of magnitude higher sensitivity than the best existing radio telescope at gigahertz frequencies. This is not a small improvement. This is a leap forward in our ability to listen to the universe, to hear the faint whispers of objects that have until now been silent. Radio astronomy may seem like an unlikely tool for detecting magnetars. These are objects that announce themselves most dramatically in X-rays and gamma rays, in the high-energy radiation that we have learned to fear. But magnetars also emit radio pulses during their active phases, and the radio afterglow of a giant flare, like the transient source detected 7 days after the December 2004 event, can persist for weeks or months. More importantly, radio observations can help us build a more complete census of the neutron star population in our galaxy, can help us identify objects that might be magnetars in disguise, can help us narrow down the regions of the sky where the dark majority might be hiding. The SKA will not solve the magnetar problem. It will not give us a complete catalogue of every dangerous object in the galaxy, but it will move the boundary of the known a little further outward. It will shrink the region of uncertainty. It will give us new eyes to see things we could not see before. And there are other instruments being planned, other observatories being proposed, other technologies being developed that might, in time, improve our ability to detect the invisible threats that share our galaxy. Next-generation gamma-ray observatories, more sensitive than anything we have today, may one day be able to detect the faint emissions of quiescent magnetars, the low-level activity that precedes a giant flare. X-ray telescopes with larger collecting areas and better angular resolution may be able to identify magnetar candidates in crowded stellar fields where current instruments see only confusion. Machine learning algorithms trained on the data we have already collected may be able to recognize patterns that human analysts have missed, may be able to flag objects that deserve closer attention. None of this is reassurance. None of this is a guarantee of safety. The magnetars we cannot see will remain invisible until they choose to reveal themselves, and when they do, the revelation will arrive at the speed of light, without warning, without prelude. The physics of the situation ensures this. No instrument we build, no matter how sensitive, can give us advance notice of an event that announces itself electromagnetically. The light from a flare and the flare itself are the same thing. The warning and the danger arrive together. But attention is not the same as helplessness. Awareness is not the same as fear. The instruments we build, the observations we make, the catalogues we compile, these are not attempts to prevent the next giant flare. They are attempts to understand the universe we live in, to map the territory, to know what is out there even if we cannot change it. And there is value in that. There is meaning in that. There is a kind of courage in looking clearly at a universe that does not care about us, and choosing to look anyway. The magnetars spin in the darkness. The magnetic fields decay. The crusts accumulate stress. Somewhere in the galaxy, perhaps closer than we know, perhaps pointed in a direction we would prefer it not to point, a neutron star sits in its long dormancy, waiting for the moment when the accumulated tension will exceed what its crystalline surface can bear. And when that moment comes, the crust will crack, the field will reconnect, the energy will release, and a beam of radiation will sweep outward across the cosmos, travelling at the speed of light toward whatever happens to lie in its path. We cannot prevent this. We cannot predict it. We can only understand it as best we are able, and carry that understanding with us as we go about our lives. December 27th, 2004 was a gift of geometry. The beam missed us. The distance was vast enough to be survivable. The ionosphere flinched and recovered, and the world went on. But the event was real, and the threat it represents is real, and the statistical certainty that more such events will occur, some of them closer, some of them better aimed, is as solid as any prediction in astrophysics. We live under an invisible sky. The stars we see at night are only the fraction of the cosmos that happens to be emitting light we can detect at distances close enough for that light to be visible. Beyond them, in the darkness between the visible stars lie objects we cannot see and dangers we cannot predict. This has always been true. It was true before we knew what magnetars were. true before we built our first telescope, true before the first human looked up at the night sky and wondered what was out there. The universe has always been violent and indifferent. We're only now beginning to understand how violent and how indifferent. But understanding is not despair. Knowledge is not fear. The right response to a universe that contains magnetars is not to cower but to pay attention, to build better instruments, to train more observers, to expand the census of known objects, even knowing that the census will never be complete, to look clearly at the darkness and note what we find there, not because we can change it, but because we are creatures who want to know. The lighthouse turns, the beam sweeps, and somewhere on the dark ocean a ship is sailing, carrying passengers who cannot know where the light will fall next. But the passengers are awake, the passengers are watching, the passengers have built their own instruments, their own ways of sensing the world around them, and they are using those instruments to understand their situation as clearly as they can. This is what it means to be human in a universe like this one. We are small and we are fragile, and we live on a planet that has no special protection from the violence of the cosmos. But we're also curious, and we are clever, and we have built machines that can detect the radiation from a magnetar 50,000 light-years away. We have measured the ionospheric signature of an event that occurred when our ancestors were still learning to paint on cave walls. We have catalogued the nearest confirmed magnetars and calculated the distances at which their flares would become dangerous. We have done the work. We have paid attention. We have chosen to look. The December 2004 flare ionized our upper atmosphere and then faded. The instruments recorded the event and then returned to their normal operations. The Magnetar SGR 1806-20 settled back into its slow rotation, its magnetic field still decaying, its crust still accumulating stress for the next inevitable release. And Earth continued on its path around the Sun, one small world among billions, carrying its cargo of life through the darkness, turning its face toward the stars. Tonight, as you listen to this, the light from distant magnetars is travelling toward us. Some of it left its source thousands of years ago. Some of it left tens of thousands of years ago. Some of it is still being produced right now in the violent magnetic environments of neutron stars scattered throughout the galaxy. We cannot know which of those beams will intersect our planet, or when. We cannot know if the next great flare will occur in a century or a millennium or tomorrow. We can only know that the universe operates according to its own rules, on its own timescales, indifferent to our preferences and our fears, and we can choose how to respond to that knowledge. We can choose attention over ignorance. We can choose understanding over denial. We can choose to build the instruments that push back the darkness, even knowing that the darkness will never be fully illuminated. We can choose to look up at the night sky and feel not terror but wonder. Wonder at the violence that shaped the elements in our bodies. Wonder at the distances that separate us from the nearest dangers. Wonder at the improbability of our own existence in a cosmos that seems designed to make existence difficult. The magnetars spin. The fields decay. The crusts accumulate stress. And we are here, on this small world, looking up at the stars, trying to understand what we are seeing. This is the human condition. This is what we do. We are the species that looks at the universe and asks questions, even when the answers are frightening, even when the implications are humbling, even when the truth is that we are small and temporary and vulnerable to forces we cannot control. The sky is mostly dark. The universe is mostly violent. And we are mostly lucky. Lucky to exist. Lucky to be conscious. Lucky to have the tools and the curiosity to investigate the world around us. The December 2004 flare reminded us of all three truths. It reminded us that the darkness contains dangers we cannot predict. It reminded us that our instruments are limited, our catalogues incomplete, our understanding provisional, and it reminded us that despite all of this, we are still here, still watching, still asking the questions that define our species. SGR 1806-20 is still out there tonight. It is still spinning in the Scutum Centaurus arm, still slowly decaying, still accumulating the stress that will lead to its next release. It is one Magnetar among hundreds, perhaps thousands. It is one threat among many, and we are one species on one planet looking up at the sky, taking note of what we find. The light that ionized our ionosphere 20 years ago has long since passed us by, continuing its journey outward into the intergalactic void. Other light is still arriving, other radiation from other sources, most of it harmless, some of it unknown. The universe continues to operate as it always has. vast, violent, indifferent, beautiful, and we continue to watch. This is not a story with a resolution. This is not a problem with a solution. This is simply the situation, the context, the backdrop, against which all human life unfolds. We live in a universe that contains Magnetars. We live in a galaxy that hosts hundreds or thousands of invisible threats. We live on a planet that has no shield against the radiation that travels at the speed of light. And we are aware of all of this now, in a way that we were not aware of it before December 27th, 2004. Awareness is not safety, knowledge is not protection, but awareness and knowledge are what we have. They are the tools our species has developed to navigate a universe that does not explain itself. And tonight, as you rest, as you close your eyes, as you let the darkness settle around you, you can carry with you the knowledge that somewhere in that darkness, the Magnetars are spinning, the fields are decaying, the crusts are accumulating stress. You can carry with you the understanding that we live in a violent and beautiful cosmos, one that does not care about us but has nonetheless produced us, one that threatens us constantly but has nonetheless allowed us to flourish. The beam sweeps, the lighthouse turns, and we are still here, watching the sky, wondering what will come next. Thank you for travelling out to the far reaches of the galaxy with me tonight, for sitting with the mathematics of danger, the poetry of neutron stars, the quiet uncertainty of our position in the cosmos. Keep looking up, keep paying attention, take good care of one another, and good night.